audible.
Is it clear? Is it clear? Hello, hello.
Yeah, yes, sir, your voice is clear. Yeah.
Okay. Okay. So, Debus Smith, we were discussing something this morning. No, I'll quickly tell you um, the brief idea of what I was, how this rotation thing can be realized in 2 dimensions. Okay. So what you do is you look at where is I cap and J cap going. They are going to points on a unit circle, and sorry, so they're going to points on unit circle, and that is perpendicular. Right. So if I cap is becoming some vector u and j cap is becoming vector v, okay, any vector z is the linear combination of I cap and j cap. Yeah. But
Yes.
now it will become the linear combination of u and v.
So we call that what?
Correct?
Change of basis, change of orthogonal basis in some sense.
So and it must rotate by, because it's a linear transformation. Alpha times this plus beta times this will result in alpha times alpha plus beta times beta, what alpha times u plus beta times v, which will be, intuitively it is just the axis is rotated. So linearly when this will rotate, and hence the vector rotate is what I was trying to say when I mentioned the subset this morning.
Yeah.
Okay.
So there is also
If
one
you
more
can
thing.
carry on, I have bad internet here.
So is the determinant of
please.
this orthonormal matrix is going to be 1. So we know that determinant is also a multiplication of the eigenvalues. So if one is outside the circle, other one has to be inside the circle. So that is the product is 1, right? So that is why we know that if anything is unequal, then also it will create imbalance and they will not stay. So that is also another intuition that we should also have.
Correct, they balance. Correct. That's also another way of seeing it. Correct. Perfect. In 2 dimension, right?
Yeah.
Right. Yeah.
So yesterday,
yeah,
what
please
we proved towards the end of the session, you were not there. We actually used trigonometry in a very first principle way to actually prove that if you want to rotate a vector by angle alpha, which is already at an angle of theta to the x-axis, what should be the matrix, rotation matrix? We also observed that it has to be, contain all the orthonormal basis vectors. That also we proved using trigonometry.
Oh, very good. So do you have maybe a PDF if you people can send? I'll take a look later, because I'll create questions based on that.
Yes,
Yeah,
sir.
sure.
Yes, sir.
You guys can carry.
I think Maria or Binay was taking that. Binay was taking.
Vinay was taking the notes. He hasn't joined yet.
Yeah.
Meet.
So, yeah, it was in his notebook. But anyway, we can do it. It's so simple. It's just like what is sine A of B equal to sine A sine B.
Can we write it down, Maria? We have people who were there yesterday.
Yeah.
Vancheshwaran here. We have Swapnil was part of. Sriram wasn't there yesterday when we were discussing that. Atharva was not part. Not there. So can we write it down? Maybe.
1 second.
Okay.
Okay. Yeah, so you want to summarize what we did yesterday, right?
Yeah.
So, so the basic idea that we discussed yesterday is that we know that matrix is a function. So, it's a function, like we can correspond when we apply an input, we can think of it as a linear transformation. It either scales the vector, the input that's applied to it, rotates it, or it does both together. That is, if you take inputs along a line, it gets transferred to some other line. So now what we're trying to do is, and we're also familiar with the concept of eigenvectors. Eigenvectors can be thought of as those vectors when applied to a matrix, your vector gets scaled alone. So we know that the basic operations that happen when you apply an input vector include scaling and rotation. So in this case, it gets scaled in the same direction. Now the question that we had, this was just for context. Yesterday's question was that when we apply, we have to find a metric such that when we apply an input vector, we preserve the norm of the vector. That is the magnitude or the distance of the vector from the origin gets preserved. So by discussion, we actually came to the conclusion that it's actually
Can we write it down?
yeah, sure.
Mathematical proof of it. Okay.
Yeah, sure. I
Tell us.
guess there's something else we should say. Yeah. So whenever we actually have a matrix, say 1, 2, 1, 3, and we have an input vector, say 2, 3, we realize that this vector is where your I cap goes to, and this vector is where your J cap. The second column is where your J cap gets mapped to. So we actually came to the conclusion that when we have to preserve the norm of a metric of a vector that's applied to it, our metrics should be of the form that each of the column vectors should have unit norm and they should be perpendicular to each other. So that was the conclusion we made. The way we observed that was that suppose we know that when we actually this vector that we have here, if it's V, so we drew a circle here. And we don't know the components. We have to guess what the matrix is. So we can assume that the matrix is something like V1 here, V2 here. These are the two columns of the matrix, right? So now what we do is that, let me do that. Devjit sir can help me, okay, because he was the one who actually, gave a really good explanation. If you want, you can take over and I can write down it.
No problem. I think the context is this, right? So one thing also we discussed that if we call that matrix M, right, the 1, 2, and 1, 3 that you have, right? Matrix is a function, and we all know linear transformation is basically a kind of a function which will map from a particular vector space to another vector space, right? So that's we already know that. Now we should always see this as a composite function. So in other words, what happens is most of the time matrix, when you apply to a vector, it will do some kind of transformation to the vector. There are two types of transformation, right? So one is where the direction of the vector will not change, only the magnitude will change. That means either it will expand or contract. That's one way. The other is the magnitude remains constant, but the direction changes. That's a pure rotation, right? So many times what will happen is the matrices will contain these elements which will apply both of these, which is change the magnitude as well as change the direction. That's most of the matrices would have that. But then there are two special cases. If we take a matrix where we don't want to change the magnitude, only change the direction, then that's a rotation, which is our current topic. The other special cases where the direction doesn't change, but only the magnitude changes. We have seen that in the eigenvalue, eigenvector conversation. I was not there, but I think it was covered by sir in earlier session, right? So that means if we start seeing matrix as kind of a composite operation of kind of a scaling plus rotation, then when we make there is no scaling, then only rotation, then that's the orthonormal condition we're talking about. When there is only the, I guess, the lengthening or shortening of the vectors, only at the magnitude, then the rotation component will not be there. So which is essentially the eigenvalue decomposition that we already know, right? So today what we're going to talk about is just the rotation. So can we all know matrix in this two-dimensional space is going to be 2 cross 1. So can we write 2 cross 1 in 2, 3, right? It's of shape 2 cross 1. So we fundamentally know we have to take a vector which is 2 cross 1 and we apply a matrix, and the resultant vector also will be in R2, which will be 2 cross 1, right? So that means we know that 2 cross 2 multiplied with 2 cross 1 will give us a 2 cross 1. That means we know that if we take a vector, any vector, let's call it, you want to call it any vector, call it A or V1, whatever it is, right? When you apply it, the output also will be 2 cross 1. So we know that from a compatibility standpoint, it has to be matrix, then the vector, input vector, then what you get is the output vector. I think that part is clear. Any questions?
Yeah, like anyone, maybe someone who wasn't there yesterday or has
Can
any
you write it
doubts.
down? Can you write it down, Maria?
Maybe I'll just start. I'll just write down a brief of the question because I think when I orally, yeah. So what we are trying to find here is, yeah, we have to find a matrix M such that if we apply an input vector, any vector to it, the magnitude or norm of the vector gets preserved. Right, yeah. So yeah, let's this was our question. So now what we'll do is we assume the matrix is M. Yeah, Devaswit sir, if you want
Yeah,
to.
yeah, sure. So let's create a matrix and we know it is going to be a 2 cross 2, right? So let's call it ABCD. We'll derive what it is, right? That you wanted to quickly prove, right? How it is ABCD. You just put, we want to find out very naturally what these are, right? Okay.
Yeah.
Now, the input vector, you give it a name, either V1 or whatever you want to call it.
Yeah, input.
Input vector, whatever is in our domain.
Yeah,
Anybody wants to suggest whatever vector you can suggest, doesn't matter, right?
A 2, 3 would work.
Yeah, okay. So when ABCD multiplied with 2 cross 3 should give us what?
yeah,
And
it should give you.
you want to rotate, right? The magnitude remains the same. So in this case, what is the magnitude of the current vector? 2, 3.
Oh, yeah.
So let's
30.
ask that question. What is the magnitude of this vector? 2, 3. So how do we remember Pythagoras theorem? It is 2-dimension, right? So on the x coordinate, you have to take 2 units. On the y coordinate, you have to take 3 steps in the y direction.
Can you
So how
Root
far
30.
down from the origin?
Root 30.
Yeah,
Maria?
root 30.
write it down?
What?
Write it down.
So the
Yeah,
square
yeah,
of the base plus square of the height and then square root of that. That's what, because it's a right angle triangle, right? That's what we remember from Pythagoras theorem from standard 8, right? So that is how we find the magnitude of a vector in 2-dimension. If it is 3-dimension, you do square each coordinate and then again take a square root of that, right? So that's usually how a magnitude of a vector is calculated. And if you generalize it to Rn, then you have to square each coordinate and then add up the sum of squares and then take a square root of that. That's typically how we find a magnitude of a vector, right? So in this case, 2 square plus 3 square, square root of 30. That means we need to do something so that way whatever we get will also get the similar magnitude. Now let's visualize this, right? So before we write it, so Maria, let's draw a circle, right? And then we have our x-axis clearly defined, right? And let's draw this 2, 3 vector. We know the circle is big, right? So this vector should be, one of the point is 2, 3. Right?
We're drawing a unit circle, right?
Yeah, not unit. This time it is not unit circle because it's 2, 3, right?
Okay. So this is
just x-axis, right? So
yeah,
this is
I mean,
x-axis.
so approximately if I take this as 1, 2, 3. Okay, root 13 is approximately 3 point something, right? So
Yeah. So the 2, 3 will lie on the what do you call it?
inside this.
Take 2, 3. It will lie on the what do you call it, on the circle?
Yeah.
Yeah, okay. So we have taken that, right? Okay. Now let's say we call that point or the vector 2, 3. We are calling whatever point. Let's assume it has some angle theta with x-axis, right? Let's call it theta, right? So again, we are going to prove from a fundamental first principle, like what is going on here, right? If it is theta, so observe that and see what will be the x coordinate, what will be the y coordinate. We already know it's 2, 3, right? You already kind of know the theta is tan inverse 3 by 2. Height divided by base, right? Whatever that angle is. But we don't know. We are taking a very general, thing. Theta could be anything, right? This 2, 3, we are taking an example. If you take any vector, there can be infinite number of vectors here. We're just picking 2, 3 for an example. But if you take a generic expression, any vector which is an angle theta, let's say that is a starting point, right? Now we're going to rotate that vector. Let's, for simplicity, we are going to rotate it in anti-clockwise fashion by an angle alpha. So what will happen visually? Imagine you are taking your geometric compass box. So the vector has a length of square root of 13 and you are rotating by a little bit extra to the left, the anti-clockwise direction. What do you expect? You get another vector. So where do you expect the tip of that new vector to be if it is not changing the magnitude? It's only rotation. Where do you expect the tip to remain in the rotated
The
position?
circle.
It will remain in a circle. Perfect.
Hey,
Alright.
should I draw the circle again?
Yeah, you can. If it to make it clear, maybe theta should be small so that way,
Yeah,
it becomes very clear.
I
Yeah.
think draw a circle using the
I think yesterday we took an hour.
option
We're
to.
trying to do a recap in 10 minutes, right? But anyway, when you've done it, then it's kind of took us an hour.
Maybe
yesterday.
there's a shapes option wherein I can actually get the perfect circle.
It's okay. Don't worry about it. It's just draw it. It's okay. There is a circle there, but don't worry about it. I think.
No. Okay, what was that? Okay, so okay, I guess it's because the service I'm on is not that good. Let me just check if I have an option for figures.
Shape, insert shape or something. Draw.
Yeah, draw ellipse. Yeah, maybe. That's better. This is better, yeah. Alright, so I can get. That yeah. Now let's okay. Yeah, I actually had a doubt. Like actually 2, 3 what's the radius of a circle?
Root 13.
Sorry, the
So
radius of the circle will be the magnitude or the norm of the vector v1.
oh yeah, okay.
Because
So then it would be
one is
like the
two
initially,
means
I got
you
confused
go
a bit.
2 units on the x-axis, 3 units on the y-axis. So that is your magnitude, right? So the
Yeah,
vector
it will be a
remain-
point on the circle, right? Yeah.
Yeah.
When I drew it, I didn't actually draw it on the circle. So like I got a bit confused there.
Yeah.
So 2 units here, 3 units here. So we have got here like yeah.
Okay. So that is vector A, and you are going to connect it to just a straight line, with arrow. Yeah. Okay. So that's our vector, and we all know our basis, the x-axis. So it has an angle of theta. You can write it down by hand, no problem.
Yeah. That's actually yeah. Now we are rotating it by an angle
Alpha.
alpha.
Yeah. So for simplicity, let's assume theta is less than 90, alpha is less than 90, theta plus alpha is 90, but technically it can be anything. It will be fine. But just for ease of proof and visualization, if we assume that, it will be very easy on the mind. Okay. So the new vector is B. Okay. So what do we expect?
This is our input vector.
A is input, B is output after rotation.
Visualization is helpful because we know that any points on the circle would have the norm preserved. That's the reason why we actually took the circle, if it
Yes.
wasn't clear, yeah.
Yes. And any point on the circle has the same norm, because that's the definition of circle. It has equal distance from the origin, right? So only thing is rotation. So alpha can be also generic. It can be anything, because theta was generic. We can take any number of examples. This is just for proof. We take any random theta, any alpha. Now the question is to rotate it to, if my A is my starting point, any vector you randomly pick on this circle, and you want to rotate it by 30 degrees, let's say alpha is 30. What should be by matrix M? That's the question, right? And what we are saying is, if you want to just rotate and not change its magnitude, you have to come up with a matrix M where this AB has to be a unit magnitude, CD has to be a unit magnitude, and plus they should be orthogonal to each other. So what we call as orthonormal. So we will prove that. If you get anything else, then it will not be. Just by observation and some algebra.
Yeah, so we have to find out A. Yeah, so the next step would be, yeah.
Okay, so
So
the
yeah.
question here is, what is the angle of beta with x-axis now?
X-axis, right? Yeah. So maybe, yeah, for east first, we know that, like, we assume we don't actually know that the coordinates are 2 and 3. It's some should we have taken a general case? Okay,
You can
so
do
like
xy also, no problem. We can take xy, that's also fine, not a problem.
Sorry. Yeah, okay. So the thing is that we know that it's 2 and 3, so we can actually express A as, like, because it makes theta with the thing. I'll just draw a perpendicular here. Yep, and the perpendicular here. It's the same as this, yeah. So we can actually write the coordinates of A as the coordinates of A is actually root 13 cos theta, comma root 13 sin theta. Right? I hope this was clear, because this is just cosine and then this is sine. Like if you're familiar, so similarly, we can actually write B as, because B makes an angle theta plus alpha, right? So that would actually be root 13 cos of theta plus alpha, root 13 sin theta of alpha, right? Is this part clear? Like, if you want, I can like show the steps, like how it becomes like. This would be more easy to understand if you're familiar with, like, we actually take the unit, something called polar coordinate, like maybe not to use the term, but is this decomposition clear? Maybe I can write a few steps if anyone wants a bit more clarity, like how we actually, like, I'll just do for A, like we can actually write, yeah. Yeah, we can write cos theta here as actually, I'll name this point P. Cos theta is actually, and this is origin O. Cos theta here would actually be adjacent side by hypotenuse, so OP by AP. And your x coordinate is actually OP. So OP is what we have to find out. And since we know it's a point on the circle, sorry, OP by OA.
OA, yeah, the hyper.
Oh, yeah, OA, yeah. Yeah, OP by OA. So OPs are x coordinate, right? This distance. So implies OP is equal to OA cos theta. And your OA is the radius of the circle, which we know because we have taken the magnitude of the circle here to be root 13 cos theta. So this is how similarly we write sine theta. Sine theta is actually the opposite side. So that would be, this direction. Yeah, this one. Yeah. AP by OA. Well, our y coordinate is actually this distance. Oh, I think I marked the points wrongly. Yeah. AP by OA. And what we like AP is this distance. Like the line is not exactly vertical, but this distance, it's a rectangle, so it's same as this distance. So AP is going to be OA sine theta. That's how we actually come to root 13 sine theta. So now we know that the norm should be preserved. And so what we're essentially doing is that we're assuming that the vector, this is our initial vector is OA, it gets transferred to a new point OB, and it makes an angle alpha with it. So since we're taking points along the circle, we know that the norm of the vector is actually preserved. We're taking some other components that would give you the same norm. So now what we're going to do is we can actually write, we don't know what the matrix is. That's what we're trying to find. I hope like you got the intuition of taking a circle, right? That's the important part. Like rest of it, you can come up with it on your own. And then our input is going to be root 13. We are writing 2, 3 as root 13 cos theta, root 13 sin theta. Now I guess it's a bit tough. And what you should get is your new point. Oh, sorry. Yep. Now this involves a bit of calculation. Maybe I'll just speed through it since we discussed this yesterday also.
Yeah,
So
you can say sine of A plus B is equal to sine A into sine B plus. Yeah, so then
So,
it will,
yeah. So cos theta, cos alpha is actually cos theta, cos alpha minus sine theta, sine alpha. And sine of theta plus alpha is sine theta, sine alpha plus cos theta. Sorry, I got the formula wrong. Yeah.
Yeah, that's correct. Sine theta
Yeah.
into cos alpha and
Yeah.
that's yeah.
That was a mistake, yeah. Cos theta, sine alpha. When you simplify by applying this, I'll write one more step, like, yeah. We can actually do the column-wise multiplication and we'll actually get this matrix, like if you, basically
Take
you're
the first
equating
row.
the
So
components.
we'll take the first row, AB, multiply with the column vector, then we'll get the first
Yeah.
element.
This multiplied with this and this multiplied with this. And you add the root 13 B sine theta and root 13 C cos theta D sine theta. So now there's something that actually kind of you might think that we obviously don't know what the matrix is of the form, but you actually notice that this root 13, it's common on both sides. So whatever the magnitude of the vector, like your matrix does not depend upon the magnitude of a vector, right? Because you can see that that part actually gets cancelled out in both sides. So whatever the magnitude of your vector, we realize that that does not have an effect on like our matrix, because it will be a factor that actually gets cancelled out. I'll do the math, I guess. So a cos theta plus b, root 13 gets cancelled. So a cos theta plus b sin theta is equal to cos of theta plus alpha, and c cos theta plus d sin theta is actually equal to, this is just math that you guys can also get on your own. I'm just writing it for the sake of completion. Yeah. Maybe if anyone has like any doubts on why we actually like, you can actually check out yesterday's recording, or like you can ask us any doubts about, like, forget the math, like the intuition of why we actually use the unit circle. Those are all mostly the important parts. Anyone has any doubts till now, or like anything that requires a bit more clarification? So now what we do is we just compare the terms, and we notice that here you have a cos theta, you have a cos theta here, you have a cos theta here, and you have a cos theta here, and here you have a sin theta, you have a sin theta here, you have a sin theta here, you have a sin theta here. So now by like just observing the common terms, we can actually come to the conclusion that your A is actually cos alpha, yeah, B is minus sin alpha, C is sin alpha, D is
Cos alpha.
cos alpha. So yeah,
Now what do we have here? Cos square
yeah.
alpha minus of minus sin square alpha. That is cos square alpha plus sin square alpha. Now this is an
Yeah.
identity we studied before, right?
So yeah, the thing is that if you are rotating by an angle alpha, your matrix would actually be of this form. It can be anything. So the important observations that we have to make about this matrix is that we notice that these columns, these individual columns, if I consider the matrix to be something like V1, V2, these two columns, this column V1, the magnitude of that is actually root of cos square alpha plus sin square alpha, which is 1. And magnitude of V2 is also sin square alpha plus cos square alpha. So we actually came to the conclusion that we can, and you also notice that these two columns are orthonormal. Like if you take the dot product, like V1 vector dot V2, we'll actually get cos alpha into minus sin alpha plus sin alpha into cos alpha, which would be 0. So what we actually come to the conclusion is that we just maybe our solution, we don't always know the alpha value, right? But we just have to observe the properties of the matrix, which are important when you want to construct such a matrix. So our job was to, like, when we started with the question, was just to find a matrix that when you apply it, it preserves the magnitude or the norm of the input vector. So what we do here, like our observations are this, like norm of V1 is always equal to 1. That is, we need a norm of V2 is also always equal to 1. And V1 and V2 are perpendicular to each other. So we actually realize that V1 and V2, the term that we use here is actually they're orthonormal vectors. So whenever we actually apply this matrix that preserves the norm of the matrix, what we're actually doing is orthonormal vectors. Ortho comes from the fact that it's perpendicular to each other, and normal means that its magnitude or norm is 1. So now what we do is we realize the properties of the matrix, right? That actually give you this this property. Something else we can observe is okay, so is there anything else left? If we apply any vector to it, yeah. So yeah. So yeah. What I wanted to say is like what I stated before was that if we have a matrix like A, B, C, D, we know that when we apply 1, 0, which is basically your vector corresponding to I cap, right? You'll actually get AB. And when you apply the matrix to 0, 1, which is actually the vector corresponding to your J cap, you'll get CD, right? This is something we've discussed before. So now what we're trying to do here is, we can think of this in another way as we are, so in this case, like our, whatever you apply, when you apply an input vector, in this case, when you apply an input vector V to a matrix, we can actually think of it as, you shift the, I cap and J cap are your normal basis vectors, or the normal reference points by which you actually try to understand the vector, right? So what we do here is essentially we are actually converting our basis vectors from 0, 1 to, we are actually converting our basis vectors from 0, 1 to AB, right? So what we're doing when we actually apply a matrix to a vector V such that the norm gets preserved is, we actually came to the conclusion that you can think of the matrix having 2 columns, right? And V1 is actually going to be the vector where your I cap gets shifted to. And V2 is going to be your vector where J cap gets shifted to. So another way we can actually think about it is that we realize that the columns of the matrix are orthonormal. So what we're actually trying to do is, we're trying to shift the basis or the reference of our vectors from I cap and J cap, to a basis vector that consists of 2 vectors that are orthonormal to each other, right? So that is, your norm gets preserved when the 2 vectors are orthonormal to each other, or we have an orthonormal basis, right? So whenever we have 2 vectors that form an orthonormal basis, we have the property that our norm or magnitude gets preserved. So that is the general property of the matrix. I guess that's what we covered. Was there anything else that I missed out, or should be added? This idea that I cap and J cap get shifted to the first column and the J column when you apply, that's actually really nice, and like it's pretty important too. So when you think of it in that way, we can actually understand that your basis is actually getting shifted to two other bases that are perpendicular to each other. It can be I cap and j cap. Instead, it would be two vectors that are perpendicular to each other in such a way that your norm would actually be preserved, right? So yeah, let me check the chat. So I guess we did a basic summary of what we covered yesterday. Anyone has any doubts or like sir, like is there anything I missed out? Like maybe anything you wanted to add?
I think, like I said, it is a special case, right? So this matrix is only doing rotation, right? We
Yeah.
have seen the flavor for eigen where it is only not changing it, only changing the scale.
Yeah.
So we should see these as related. So matrix can do everything. In this case, we're just focusing on the proof of rotation. Similarly, we can, if we have not done the proof, we can do the proof of you multiply a matrix with a vector that will give you a scalar times a vector. That's eigenvalue. Here we
Yeah,
are
that's right.
multiplying matrix with a vector to get a vector. In the other case,
Yeah.
if you notice, there's a beautiful property where you take matrix, some nice matrix A, when it is multiplied with the vector, it will give you a lambda, which is a scalar times the vector. So that on the right hand side is what we call as the lambda becomes the eigenvalue, and the other one becomes the eigenvector. So that is also another special case, which is the exact opposite. I mean, kind of parallel concept to this. And most of the time, the matrix A will consist of both of these. So if we start seeing that, anytime we apply a matrix, we look at, is it changing direction or is it changing magnitude? Many times it will be both. You can observe it physically, right? So this is what we discussed. If you take an object and you apply a force, right, then it will, in the outward direction, the length of the scale will increase. But if you are only taking it and doing a rotary motion, right, how you move your clock, right, you're applying the force at an orthogonal to the vector, then you know it is going to rotate. It is not going to impact its magnitude. It's trivial. You all would have changed the clock of your wall clock. How you apply the force? You apply the force perpendicular to the minute hand, right? So we all, should relate it to something physical that we have done. But if you have to extend, you take the elastic and you apply a force which is parallel or in the same direction as a vector. Then there is scaling, which happens for eigenvalue and eigenvector, right? And then if you do both, like if I do it in an angle, then there'll be some component which is in the direction of the vector. So that will be the scale component, the other one will be rotation component. If you kind of think like that way, then I think it's easy to visualize that typically when you are taking a matrix, which is essentially nothing but a function, nothing but a linear transformation, there'll be a rotation component and there will be a scale component. When there is no scale component, then there's only rotation component, we just discussed, and we also gave a proof. If there is only no rotation but only scale, then that's the other thing we discussed. So ultimately, I think all these things will, kind of are all interrelated. They're not independent. They're all derived from the same matrix, which is essentially the linear transformation, which is taking a vector from one vector space to another.
Okay, we can continue with Linnal 75 then. Just a minute, I'll be back.
Srivinay, every rotation matrices would actually have eigenvector and eigenvalue, except that there will be special properties, right? Any matrix, if I create a matrix, rotation matrix, so we know they're orthonormal vectors, so it's like a basis, right? So their eigenvalues intrinsically, what will happen if I give you a matrix which is 1 0 0 1? Let's take the typical standard basis for our R square. What is the determinant? Determinant is 1. We know that, right? So determinant is 1. We know there will be 2 eigenvalues and 2 eigenvectors. So if you solve the equation, what do we find? What are the, if you take a matrix 1 0 and 0 1, the standard matrix, what would be the eigenvalues? A minus lambda I, the characteristic equation, we can,
Lambda will be 1, right?
there'll be two lambdas, right?
Yeah, both of them will be 1. Is that
Both will be 1, and we know lambda 1, lambda 2 should be equal to the determinant. So we know 1 into 1 is 1, right?
Yeah.
So both will be 1 and eigenvectors will be orthogonal to each other, right? So similarly, so this is why for these 2 by 2 dimensions, they would be both the lambda will be equal, and the basically it's a change of basis. Basically, that's what going to happen, right? So, but yeah, the rotation matrices, the determinant will be 1 because it is not doing anything to the scale. That is the observation. Similarly, for the
What I would like to ask is, we know that Q is a rotation matrix, but is Q transpose also a rotation matrix?
interesting. In fact, that is actually the decomposition that Sir must have discussed. Any matrix, square symmetric matrix, it can be decomposed into Q lambda Q transpose. I think that was discussed.
Yeah, it was discussed, and here comes the idea. We know that what essentially each matrix does is it scales up input and changes its direction.
Yes.
But if we see a matrix as a decomposition of Q lambda and Q transpose, so essentially we need to see that we know that Q will essentially we just change the direction, nothing else. Magnitude will
that means if a matrix A could be rectangular. This is actually SVD, right? So if you take n cross m, a rectangular matrix, and do a decomposition, the Q matrix will contain all the orthonormal vectors, each one of them having unit magnitude, and they will contain the direction of the input space.
Yeah.
In the one in the middle will be diagonal matrix, which will contain all the lambdas.
Only the scaling.
Only the scaling. Got it.
Yeah.
And then the resultant will be another Q transpose, which is actually inverse. That will have the dimension of the target space. So if I'm going from Rn to Rm, the first one will be n, but the other one will be m, right? So it is just to, but they will have a similar property. So essentially, intuitively, what is happening is, again, going back to the same point, a matrix is composition of rotation and scaling. All you've done is you're basically, if somebody tells you 2x plus 3y, how do you express 2, 3, and then xy, right? So it is kind of separating the direction and magnitude, right? So you're kind of decomposing it. One will give you the direction in life, other will tell you how much. It's true for life also, right? We were joking yesterday, right? If everything you're doing right, you just need to accelerate, then you will increase your magnitude. You just study a little more hours. But let's say you're reading wrong things, you have to first change your direction, read the right subject, and then after that, you worry about the magnitude later on, right? So first thing is to do the right things. And after that, you increase your efficiency, which is the scale.
I need to think about your two statements more. I will think about it. Like that it maps input space, it maps output space. But question still remains, like Q transpose. Does is Q transpose also a rotation matrix only?
Q transpose is in fact Q inverse.
Yeah. But that for that it's a special condition now when Q and
that is the property of orthonormal.
It's simple, isn't it? If a matrix transpose is inverse, then that matrix is orthonormal.
Correct.
By definition. Nah?
Yes.
I repeat, if a matrix transpose is also inverse, if and only if the matrix is orthonormal, right? Now, Q's inverse is becoming Q transpose, which means Q transpose is Q.
Right.
Which is also its inverse. If Q's inverse is Q transpose inverse will be Q. So Q transpose inverse is also its transpose, and hence transpose of a matrix is its inverse, and hence Q transpose should also be orthonormal.
Yeah.
It's a straightforward mathematical result, but in general, this is true because the inverse of an orthonormal matrix is always orthonormal. That you can see it straightforward. Inverse ही हो रहा है ना? देखो angle change हो रहा है. Inverse means that angle वापस आ रहा है. If it's theta, it will be.
So in our example, we rotated the vector which is at angle theta. We added alpha, so it was a theta plus alpha. Now you're coming back with a minus alpha because you're going a clockwise direction. That's still what it is. that's the geometric intuition behind it. So you are kind of applying another matrix to take it back to the original position. So it's almost think of like, I rotated a vector from A to B. There's another matrix that will be applied to B that will bring B to A.
That is nothing but the inverse. Yeah.
Yes,
There's nothing but rotating it back. So
correct.
transpose.
So this finding is also interesting now. Like we can always see a matrix as a multiplication of Q lambda and A transpose, or Q transpose means Q inverse. And we also know that they are orthonormal. Therefore, they just change the direction. So essentially, here one conclusion is only lambda that is changing its magnitude. So if now we can scale up and cook up a perfect matrix that we want.
And it also gives us a lot more interesting things. If it will give lambda 1, lambda 2, they are not equal, in case of unit basis, that 1001, what Srimani was saying, we'll get 1, 1. But we'll eventually find lambda 1 is biggest, lambda 2 is the second largest, dot, 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 lambda n. Then you'll notice that the first few ones capture most of the information, right? So if I ignore a certain part, the bottom part of lambda, I will still be okay. That is relating to a dimension reduction, reconstruction error conversation, missing value imputation. That's the link hook to the other problem. Sorry, Maria, you're speaking. One mute.
Oh, sorry. I was wondering. Okay, like yeah. Yeah, so in the singular value decomposition, you have Q lambda Q transpose, right? So what this like when we actually think of a matrix, like you mentioned that it does scaling and transformation, right? So we can actually decompose any matrix as Q lambda Q transpose. So this lambda is actually the part that does the scaling, right? And Q is actually the part that changes the direction. So when we decompose a matrix, we can think of it in that way as well.
Yeah, and it was always true because the I cap, J cap. So you look at it was 0, 1 and 1, 0. When you do a matrix, you take 2 in the direction of X and 3 in the direction of Y. That's exactly what it means. And it is
We're
rotating.
starting to link together.
Yeah, so now it is rotating. If they're similar, then it is rotating at 45 degrees. If it is 3, 2, then you know it is tan inverse 3 by 2. Because it's rotating, going more in the direction of Y than X, then you know it's going to be more than 45. So that's the intuition, right? So you're going on X axis more units, then it will be less than 45. That's the, so depending on, so you can control the angle by making X and Y different, right? So you know the intuition that if Y is more, it will be more than 45. Like if we're talking about first quadrant, right? Rotation, right? So that is kind of the relationship, right? So, but if you don't want to rotate, you clearly know that one part will be 0, right? So
Yeah.
Able to see the matrix as Q lambda Q transpose. Q is kind of rotating it in one direction, and we know Q transpose is the inverse. So, in the sense, doesn't it feel like we are rotating it and rotating it back? So, how come the rotation?
see, actually not rotation. So typically what is happening is, if you look at the dimension, the SBD is applicable for a rectangular matrix also.
Yeah.
Right?
Yeah.
So assume n cross m. So when you decompose a n cross m, notice the dimension of the first Q and the second Q. They are not the
Are
same.
different. Yeah.
In the middle, it will be, so n cross n will first give you the first Q is n cross n. The middle is n cross m. The last one is m cross n. You got it?
Actually, yeah, you take it as Q1, Q2, I guess, like when you have a rectangular matrix, yeah.
So that means
They're not same, yeah.
So if I'm going from my input, I have got 10 features. So I'm going from R10. My target, if I'm actually going to a different R8, right? So which is So then the other Q will be, 8. I mean, because I got more observations, right? So more number of customers, less number of features. Typically, N is greater than M. You got it? So my but the number of vectors here are different than other ones. So just notice the dimension of those decomposition. So if I'm multiplying 3, how they're compatible. So to get an N cross M, what are the 3 things I have to multiply to get N cross M? That should give us the answer.
Kind of, I mean, so in the case, if it happens to be that it's a n cross n, it's a square matrix, then does it mean that we're only rotating and rotating back? I mean, I just want to correlate the idea.
Yeah. That's again a special case. This is why when it is equal square and then symmetric, the spectral theorem tells us there are very nice properties. So this is why we all love, like A transpose A is a square symmetric matrix, and that's why when we apply a decomposition using spectral theorem, it gives us beautiful results, right?
But Q doesn't have to be symmetric, right? Okay, say I take a square matrix which is not symmetric, Q doesn't have to be symmetric then, right?
Right.
Then, I'm just thinking about what it means when the rotation and rotation back happens. Does it mean that when the scaling happens and then the rotation happens, it kind of does something else?
We I think kind of giving an example, like what do you mean by an inverse, right? So that was our discussion, right? So in case of rotation, you are kind of staying in the same space. We are in R2 and you are remaining in R2. You're only rotating, right? So that's what we are, at least in this example, right? So in that case, your magnitude is not changing. So if I rotate a vector by alpha, I get this matrix like cosine alpha, minus sine alpha, sine and all that. Now, if I want to rotate it back, so you intuitively know that I have to go in the opposite direction. So wherever is alpha, you rotate with minus alpha. I mean, you plug in minus alpha. Now, sine minus alpha is minus sine alpha. Cosine minus alpha is assuming it's a first quadrant, right? So you plug it in, you will get the matrix. So apparently what you'll find, you observe the first matrix and the second matrix, observe the properties. You'll notice that it's just a transpose of the previous. Yes. That's first observation you'll have. Second observation is if you multiply these two matrices, you get identity. That means the second matrix is actually the inverse of the first matrix. So this is what Sir was talking about. The orthonormal matrix containing orthonormal vectors have a special property that the transpose itself is also its inverse. So if and only if, right? This is a property. So this you can prove. So in both ways, you can find if this is the condition, this is what you'll get, and this is the condition. If you get a matrix like that, then you can prove that they're orthonormal, right? So you can go in both directions.
Yeah, I understand that, but okay, Maria, can I just ask the question? So can you just write a square matrix, right? Just in the next page, can you just write a square matrix? And this square matrix, when I decompose it, I will have a Q which is a orthonormal basis, and we know we will apply Q first. Oh wait, let me think about it. Q, yeah. So Q lambda Q transpose. If I do it, this means I'm applying rotation first, scaling, and then applying the rotation again. Same rotation back, right? Because that's kind of the inverse, right? Not same rotation, but like the thing that brings me back to the same place I started. One second. Yeah. So does that mean that no rotation takes place?
I think the order is important. Is that the reason why you're getting scaling and then rotation? So
I mean, I know that it is not the same. I know that there is some rotation, even if it's a
yeah, but the
random square.
explanation.
So write a Python code. We have NumPy. These things are like the print. You store, decompose, store all the components, and then print and observe. That's the beauty of this, right? So we can open a Jupyter notebook or whatever, give the matrix A, and it's a very generic, right? So in NumPy lineage, we'll get all these things. If you're interested, of course. Otherwise, we can take it offline.
Yeah, we can try it out, but I haven't to help me out with NumPy.
NumPy linear algebra.
Then I'll open Jupyter Notebook.
You want me to do it on
Yeah,
Colab?
you can do it if it's
I'll just, I had the code open, so I thought maybe.
Very good. So you are already in the right vector space, Srivinay.
We took quite a few.
Understanding my understanding, anyway.
My bad.
Or verifying my understanding. Anyway, I'm just messing with
Yeah.
you.
singular value decomposition, right? That's what we're.
Yeah, so 1 to 3, 2, 4, 5, 3, 5, 10. Is it somehow? It's not. I'm not sure. Okay. 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 Sorry. Is there a NumPy a method, sorry, a function to decompose a matrix? A dot decompose. I guess. Not sure. What is it?
I just reading. Yeah, there is NumPy SVD.
Analysis of SVD of A. Okay, what does it output?
Full matrices is full rank, I guess.
We got two matrices. We got, okay, so we got the first matrix, we got the, I think these are the eigenvalues, and this is the second matrix. And is this a symmetry matrix? Is this the transpose of the first matrix?
Comma.
Sorry. And oh,
Yeah. Actually, your lambda is a diagonal matrix, right?
yeah,
With
yeah.
the these are the eigenvalues, I guess.
Yeah, these are just the eigenvalues. So let's do one thing. If I take A1
E
to
into
be,
Q, right?
yeah. If I make A1 as this and A2 as Q transpose, right? And then I take a random vector, which is np dot array of 1, 2, 5. Let me apply A1. Is it at 3?
Yeah, that's correct.
Yeah. And what if I do A2? To get back 1, 2, minus 5? Am I doing something wrong?
Fine.
Hmm?
Can we actually check if the matrices are symmetric? It should be,
I
right?
can check it. I mean, the diagonal entries are the same, minus this, right? And 0.129. Oh, this is minus. Why? Is it SVD not the same as QR value decomposition?
I don't know what Q are.
Oh, it's different.
No, it's different decomposition. There is so many LU, QR,
Yeah.
Cholesky. There are so many decomposition, right? So
Okay, Culex. I haven't heard of like I
yeah,
don't know exactly what they are, but I've heard of these Kuleski. KU. What's the spelling?
Cholesky decomposition is different. There are so many metrics decomposition method. What is more important is each decomposition has its own meaning. It helps you to achieve certain objective. What is your goal? Is it dimension reduction? Is it to solve the system of linear equations? Depending on your objective, then you decompose to help you to move in that right direction. So it's almost like, as a data scientist, we have multiple tools in our hand. Depending on whether you want to drill a hole, then you will take the drill. If you want to put a nail on the wall, then you'll take the hammer, right? So
QR decomposition is having between
So why we do SVD? I mean, I think sir must have covered it, right? What is the ultimate goal? Why? How? What is the end game for SVD? How does it help us in real life?
Singular value decomposition.
I know there are 5 types. We talked about it. Why use SVD and how it is going to help us to solve what real life problem?
Is there matrix, right?
Sorry?
Singular value decomposition? Or it's something else. I'll check that out.
This eigen decomposition is, it will give you the eigenvalues and eigenvector. This is actually another one. This is very interesting. Actually, probably one of the most important ones.
What's the property of Q and Q is an orthogonal matrix. Is that to how you singular value decomposition gives you? Or
orthonormal, right?
No, the matrix is called orthogonal, right?
No, it's still called orthonormal. Is it? Or maybe.
Any help that you people require? I
Yes,
can
sir.
help you with
Yes,
voice
sir.
note.
We were discussing, we were trying to understand, uh, I mean, we know that a matrix consists of scaling and rotation. So we were trying to interpret singular value. When you apply the matrix A, you can decompose that in like Q lambda Q transpose, right? So we're trying to
Correct.
interpret that in terms of rotation and scaling and understand how the decomposition and actually gives you both rotation and scaling. The scaling factor is actually achieved by that lambda term, right? So like
Correct.
we had a few doubts in that.
Sir, in the southern part of India, we use a lot of batter, right? That's kind of a matrix. That is used for idli, that is used for dosa and many other items. I think some of the
Correct.
from North India may not understand it. If I
Mhm.
want to use idli, I'll put it in a circular thing and I'll apply steam. If I want dosa, I'll do something else, right? So similarly, matrix, depending on what I want, I'll do a decomposition because that each decomposition has its own objective and it will help me to answer a certain question, right? I think
Right. Correct.
we learned SBD, we knew that it will decompose a rectangular matrix, which is beautiful because most of the things we learned was on square, symmetric, nice properties. But SBD is very powerful because you can take an image which is 16x9, like a movie image, and decompose it, and we can use it to maybe compress. So that means it's a dimension reduction we can use it for, or maybe there are other. So I think applying each decomposition method to a particular real life application will help us understand instead of mindlessly doing it, learning something, where it is going to help us, right? So then there'll be better
Correct.
understanding of these methods. So that is what we are
Correct. So yeah, basically your QR is used in least squares. It energizes it puts your least squares method on steroids, because if you know the QR factorization, computation becomes very easy. If you people want, we can look at that.
We get an orthonormal plus an upper triangular. That is very similar to the condensation method, right? You kind of so you can back substitute and get all the answers, right?
Yeah, sir.
Correct.
So yeah, we actually tried a code in NumPy. So when you decompose a square matrix into Q lambda Q
Okay.
transpose, right? You're supposed to get two symmetric matrices at both ends, right? Where Q and Q transpose, no.
Right, provided your matrix permits it, right?
Yeah, but when we tried it out, we didn't actually get
Yeah,
two
what matrix
symmetric
did you take?
matrices.
Did you take a random matrix
Yeah, we took a random matrix.
of dimension
3x3.
1, 2, 3, 2, 4, 5, 3, 5, 10? Okay, show me.
So SVD does Q lambda Q transpose, right? So this is our
For a
Q.
square matrix, yes.
Yeah, but I can see that the last entry is being negated. I'm not sure why.
Because maybe the matrix has complex eigenvalues.
Okay.
Let's see, 1 minute. The eigenvalues are not complex, 1 minute, but all of them are minus. Okay.
We'll try 2x2 case.
1 minute. Q transpose be likh raha hai wo, but why is it showing 1 minute? There's some problem there. Wait.
Q transpose.
so we have
The
to make
printing is what we are giving it actually. Like
minus point 1 to कहीं पे नहीं है ना वहाँ पे.
yeah, last entry. Oh, point.
There's some negation at some places, like
Is it skew symmetric? Like A equal to minus A transpose.
maybe I have to check what the output actually is giving you.
No, multiply this and then check whether you get back the matrix.
That's what I tried, sir. I tried to take a vector and applied Q, and then I applied Q transpose. So I got 1 to minus 5 instead of 1 to 5. So I just wanted to check what the HVD's output is. What does it output actually, sir?
This is right. So maybe now this is giving, wait. This is giving your U sigma V transpose. Okay, SVD is slightly different from the eigen factorization. Okay, there should be other kind of factorization. Can you check?
Yeah, that's whatever.
This
eigen decomposition. Yeah, try eigen decomposition.
So it will give you the bunch of lambdas and eigen vectors.
Vectors. That's right.
SVD, the case when you have rectangular
No. This
matrices.
I think is not a full rank matrix. That was the problem.
So find the determinant of this matrix and the one that random. Make sure it's full rank.
This one, the one we have.
I think there's an option whether like there's a parameter you can give it when it's not full rank. Like there's something in the documentation.
I see.
I make it 11.
Yeah, even then you're getting the negative.
Even then you're getting negative. Okay. No problem. What you guys do is
Can we use modulus? Maybe try using it.
Sorry.
no. This is your U and V. They are different matrices actually.
Okay.
U
Not
sigma
what-
V transpose.
Yeah.
Yeah. No. Try to take something which is simply its eigen values itself. Eigen decomposition nahi hai wahan pe. Is there any eigen decomposition function in NumPy? Check.
Yes, it is. It is actually AIG.
EIG will only give eigenvalues, I guess. Huh?
Yeah.
What about the matrix U?
U is an
This is the one EIG. Yes. It'll give
Oh,
you
you get U also. Okay, let me try this. Okay.
This is
Yeah, you should manually compute the U transpose then U dot T.
It's similar, but it was like case like normal eigen decomposition is for square matrices, right? So
Yeah,
similar
see,
value
there is some correct. They do some numerical computation and it ends up becoming like that. Let's see if this multiplication gives us that. Then it answers the question. Let's go slowly. What we'll do is first we'll do the S lambda S inverse, S transpose rather, and then check if it is.
Yeah. I think eigen decomposition
Wait a
for
minute. Wait a minute. I think they were not normalized, I guess. Let's see, wait. Let's see. You do the multiplication and then check.
Yeah, so I did lambda comma U is equal to NP dot lineage of eigen of A.
Okay.
And let me bring that down. Yeah, and then I did this. So U transpose is this. I applied U on V and then applied U transpose on the output and I got 1 to 5 again.
yeah, so
Which means it's right for that,
Yeah.
right? But you should put the lambda in between, right? No, just do U dot lambda dot U transpose.
sure.
Should I put at? Okay.
Yeah.
At U transpose.
Get the
Enter.
matrix back.
Are you getting it back?
Yeah.
I'm getting a no, I'm getting a
So
3.
why display U? Display just U. Okay, display just U transpose.
Maybe it has to be this. No.
Yeah. I think the order in which it's getting multiplied should matter, no? Still, it should give you the right answer.
Oh, our lambdas are 3 cross 1 instead of a matrix.
Yeah. Make it a matrix then.
Okay. Oh,
You have to store the values in a list.
No, take an identity matrix and multiply that with lambda, that's all.
It's a bit different in the values, right? It's not a scalar matrix. It's just diagonal. So your diagonal entries are different.
That's what, so identity element times that will give you
So for
Yeah.
identity,
lambda
So-
times identity.
How do I
identity
get-
is np.i EYE bracket 3.
Am I right? Wait a minute. No. What am I saying?
Different eigenvalues will be there across the diagonal, right? It's not all the
Yeah.
values.
That will give you another column vector. I'm just talking nonsense. Sorry. So you should
I can do
work
lambda.
lambda of I, lambda of 0.
Okay, I can do that.
Comma 0, comma 0. Yeah, exactly. Then lambda of 1. You should do a numpy of this, by the way. Otherwise, it becomes a list. No, it should be an array.
Yeah.
Zero lambda 1 0. Lambda 1.
0 lambda 2.
0 lambda 2.
It gives it in the same order, I guess, right? Like greater to. Yeah.
So there is a trick. If you do np.i EYE 3, you'll get a
Identity matrix.
with all the diagonal one. That's a quick one to do it. And then
But how do we multiply that with lambda is the question.
lambda into npi 3.
On that give you
Diagonal values are different, right?
That's right, no? That's right, no? That's all, no? 2 cross 1, that's right. That's what I was trying to say.
this side. Okay.
That's right. That's all we
Yeah.
need to do.
Okay,
Identity
okay.
times lambda. ठीक है. Anyways, so now that we have this, we can
Right,
continue.
the lambda is a vector, not.
Yeah, if you put lambda on the right side, it gets a column
Yeah.
vector. If you put on the left side, it
Yeah,
gives you
that's correct.
whatever they were supposed to say. Yeah.
Yeah. We just had to do that. Yeah. So yeah.
Yeah, 1, 2, 3, 2, 4, 5, 3, 5, 11. Yeah.
We're getting right.
Yeah.
Yeah.
Now look at the SPD part and then try to multiply and see whether you get the same thing. Now to get the SPD of this. I think you will get the signs might get cancelled there.
What does this give you? U lambda and this is not lambda, is it? Should be lambda.
It's the vector with all the eigenvalues.
Yeah,
Singular values. What is it?
So
So
Lambda only, is it?
Big matrix has that array times I, right? So now let's see. Dot SVD of A of 1 times I. What is the syntax to generate an identity matrix? What's the set something?
np.i
np.i
then within bracket,
into np.i. Yeah.
within bracket 3 because it's a 3 dimension.
So wait on.
I times lambda.
I means
Or
EY,
it's lambda times np.i, right?
bracket 3.
Bracket 3.
Yeah.
So it should
It's
be
actually I.
Yes.
Oh, I thought it was capital I.
No, it's
Yeah.
it's actually many Python questions people get asked. Somebody who has done it will be able to answer it. Otherwise, most of the people will say.
Oh.
Yeah. It's a weird syntax.
I think it has to.
Right, Srivani.
Still think the recurse will
I don't know why I'm still getting.
Just display NPI and then lambda separately. Let's see whether it is properly done. Just display NPI.
Yeah.
And display lambda. For NPI is
3 cross 3.
seems to be a list, no?
A list of lists. Yeah, I guess.
Yeah, this is not a. Yeah, the data
Yeah.
types are different, I guess.
A NumPy nested array, right? So I mean, it's an array. I think that's correct. Matrix would be essentially array of arrays, right? So each row is an element.
But maybe the NumPy multiplication doesn't work when you get the list like that. Like
NumPy is
This
the
looks good. Class NumPy array. It's all good. Yeah.
that is best for matrix computation. There's nothing else. It exists only for matrix and math. Maybe the only other thing is SciPy. That's the next best thing compared to NumPy.
Okay.
I think
Does not add this.
can't hear you, Maria.
oh, it's like, is it? Oh yeah, sorry, my network was bad. Yeah. Yeah, you gotten the answer, right?
Yeah, so it's lambda into
Times NPI. Yeah, I saw.
okay. And now we want to do the same thing.
U into L matrix times V.
Where do we transpose or V?
Just
We
V, right?
transpose. We transpose. Or was it already in the transpose mode?
Yeah,
Okay.
I'm
It
not sure.
wasn't.
Maybe.
Okay. 1 1 minus 3c. It's not coming.
Yeah. Maybe it's
Oh,
already
1 2
done.
3 2 4 5. It's correct, is it?
Yeah.
Yeah.
Can we
Okay. So
just
now
check
I think.
if
No.
U
I think
and
I
V
got
are?
it.
Yeah,
No, I
sure.
think I got it. What they're doing is this is another possible factorization where signs get multiplied and signs become plus in the appropriate places. That's all. See, the values are the same. Plus or minus are changing, correct?
Yeah.
Yeah, can you just print U and V and just check because
The signs are
yeah,
changing.
it's the same as we got. Yeah. Okay.
If you do U transpose and minus V, they will be similar.
Yeah, try U transpose times minus V if you're getting an identity.
Skew symmetric, right? So
Transpose minus.
U transpose at minus V. Like if it's skew symmetric, then that should be the
No,
case.
was this skew symmetric?
yeah.
I don't think so. Was it skew symmetric? It just had negative signs in some places.
Yeah, the transpose is the negative of that.
Sorry, U at minus V, not U transpose at minus V. Still not.
Actually, what I'm saying is U transpose should be equal to minus V. That's what we want to check.
Okay.
Keep it separately. U transpose print and then minus V and then see compare if it looks. Yeah, exactly. That's Bharat is putting that in the chart. Minus V. Yeah. Let's see the same.
No,
Oh.
they're not.
That's all. See, the numerical computation is giving us a different kind of factorization. That's all.
So we have to study the API, NumPy API documentation.
Yeah, that algorithm that's a numerical algorithm which probably gives you some U and some V. But you are right. U is the eigenvectors of AA transpose. V is the eigenvectors of A transpose A.
It's funny that SciPy also has another. So if you change from NumPy to SciPy, the first one, click SPD. Most of the people use that in scientific community. So this probably
It's all the same LAPACK routine, no? That's what they had mentioned.
Yeah, it's only on top of NumPy basically. Yeah.
It's the same, I guess. Now everything stands on this Fortran code in Fortran or C code
C.
written in LAPACK routines. LAPACK. वो वहां पे था actually, just saw it as scrolling.
Correct. LAPACK driver. GSTD.
Okay, it's some numerical algorithm related problem, I guess. So we can do one thing. Take the matrix A and compute the eigenvectors of A trans. Compute it. Find the eigenvectors of A times A transpose.
A times A transpose, is it? Okay.
Correct.
Oh, A times A transpose. The left, what did that call as?
Be a symmetric matrix.
Yeah. Yeah, find this out. Now do it for A transpose A.
We had a discussion on this also. N cross M and
One is N cross N, one is M cross N.
we talked about.
Check if this is what you are getting on the left and right side of. Are they the same here? Are they're the same here?
That means A transpose and A are equal, right?
No. A transpose and is A asymmetric? No, I don't think so. Just
No, it
display
wasn't.
A.
No, it was no. We took a random one. It wasn't symmetric.
By the way, eigen values are different, as you can see, right?
They will be.
Now even eigenvectors are different, no?
No. Sorry, I mean this I'm not sure does it really.
See, star is the dot product, and at the rate is matrix multiplication. So at the rate should be used for matrix multiplication. For if you want to do a dot product, then you do the star.
Yeah, right. At is how it's done. What is it showing? Is it the same? It is showing A times A transpose. A transpose
I
times
think A and A
some-
transpose are equal here, right? Can you just
Is
print A
it?
transpose?
Symmetric, yeah.
Oh yeah, you're taking a symmetric matrix, obviously.
Sorry.
It
Oh,
was a very
yes.
big coincidence. Like we didn't plan that.
Yeah.
In fact, we discussed this particularly, sir. We are discussing about the collaborative filtering, which many of us, when you go to Netflix, Amazon, the automated recommender system, right? So there are two ways we can do it. So I can, if we are focusing on rows, which is customers, I have a new customer. I can see if a customer is equivalent to somebody else. So then I'm doing a analytic matrix, which is user. But if I'm interested in giving a recommendation based on the movies, then I'm focusing on movie cross movie, right? I'm analyzing similarities between movies and then I'm recommending you. So this is where the A transpose A and A transpose comes into the picture. Except I do A transpose A, then it is M cross M, which is movie. The other one, A transpose, in that case, when N is large, will be huge space. It's computationally a lot more expensive compared to, they call it user item.
This discussion sort of started because we wanted to the eigen decomposition, right? So when you're doing Q lambda, Q transpose, how is scaling and rotation actually happening, right? We wanted to
Yeah.
figure that out, right?
I don't know. I don't know why I can't see it very clearly. Since Q and Q transpose are inverses of each other, doesn't it mean that it's going to like nullify
Yeah,
the
just
rotation?
scale. Yeah.
Sir, I wanted your.
No. See, for this we should cover what is called similarity transformations, which I'll cover. It's a slightly advanced concept. Any matrix of the form S A S inverse.
Mhm.
If a matrix B is equal to S A S inverse, these matrices belong to a particular category. So you cannot call. Can someone write this down on a sheet of paper?
Okay.
Yes, sir.
I think Freeway has it too. Yeah.
Yeah, call a matrix M is equal to S A S inverse. We have this temptation of cancelling of S and S inverse, right? But in matrices, it doesn't happen.
Yeah.
Okay. In real life, in real numbers, we can always cancel the two real numbers, S and S inverse, right? Even in the matrix sense, you can cancel it in the sense that your M and A will have some properties. Okay. Can you guess what are those properties? A and M will have the same eigenvectors. No, M equals SA inverse implies M and A have same eigenvectors.
What is SA and S inverse? What is S and A?
No, anything. If you can write a matrix M as SA S inverse, then M and A will have the same eigenvectors.
And S and N is inverse must have orthonormal properties as well.
Correct. No, that is in this case. It need not be true in all cases.
Yeah, I mean, if it can be expressed, we can verify that.
So this is the general case and your equal decomposition, that's the special case of this.
Not audible.
I'm sorry. Okay.
So if
Am I
M and A
audible now?
Yeah.
Yeah, so I mean, Q lambda Q transpose, is that the special case of this general decomposition?
That's right.
Okay.
And this would be SVD.
Yeah, if your S is an orthonormal matrix, that will be your SVD.
SVD we use for rectangular matrices too, right? So
Can't hear you. Can't hear you.
Yeah, sorry. Yeah. Yeah, so SVD we use for rectangular matrices too, right? So how does it work then? Because the inverse itself is different,
Yeah,
right?
so the idea is rectangular matrices are actually square matrices in a disguised form. So whenever you see a rectangular matrix, you find it's A transpose or A transpose A.
Yeah.
When you observe these two square matrices, they will carry some of the properties of rectangular matrices will be shared by A transpose. The rest will be shared by A transpose A. So that's the reason why we SVD is about decomposing a rectangular matrix. Well, the theory of the square matrix is being used there.
Now, like, but I didn't understand it much, so that's right.
Cover page of Gilbert Strang book, Fundamental Four Subspaces. I think.
I'm actually having like this week's lecture actually consists of SVD, but the lecture was not that good.
Which subject?
MLE.
No, we will do it in detail. So we should reach there. I mean, there are some bridges that we should put and then reach there. As of now, as long as you understand QA, Q inverse, that's all is the idea there. QA, Q transpose rather. That's all is the idea. Okay. Writing QA Q transpose for rectangular matrix, we do some jugaad. When you do that jugaad, your Q becomes some other matrix. That's all. See it like this for the time being.
Yes.
Where your basically your Q is your eigenvalues of eigenvectors of your A transpose Q inverse ki jagah mein you put V, right? V transpose rather. That will be the eigenvectors of A transpose A. Yeah, maybe I'm telling the other way around. You can just write down and then pen.
Very, very fair, yeah.
No, it is other way around. Like
Other
A
way around.
transpose A
A
gives.
transpose A will be on the left.
Yeah.
A transpose will be on the right. ठीक है. Is what you have written the right one? Whatever you're writing now?
Yeah. So left would be U.
Transpose.
A transpose A should be V, and A transpose A should be U, and A transpose A. Oh,
Yes, you watch the lectures for MLF, you know it.
So this is where, you know, your observations are all. The quiz question will be what will be the dimension of all the Qs, right? So you're going from number of rows and because it's rectangular, right? Typically,
A
in
transpose A gives U.
No, it's easy, right? So what you write is write the rectangular matrix A is equal to. Okay. You go on.
I think it's not V transpose because V transpose is same as U, right?
Like
No, it is not A transpose.
how,
It is the eigenvectors of A transpose.
how I
Okay,
remember is
okay.
like if we multiply A transpose from the left side, we get a right hand side matrix, and if we multiply from the right hand side, we get like U
Oh,
that is
no,
on
guys.
the left.
No. We don't write A transpose. U is not A transpose. U is the eigenvectors of A transpose.
Yeah. But for remembering, I just.
Acha.
So the real life interpretation is when I'm taking a real life data of movie viewing habits of a lot of customers, right? My matrix, the rectangular matrix means if I got 1 million customers on 1,000 movie, my N is million and M is 1,000 movies. So when I do A transpose A, that means it will be movies cross customers, customers cross movies. So I get a movie cross movie. That
You
means
take the lesser one, right? 1,000 cross 1,000 in this case.
correct. So then I'm analyzing the similarities between movies. Or if you think of the e-commerce, I'm looking at similarity between products. So A transpose A allows us to, in some sense, relationships between the columns in the rectangular matrix. Whereas A transpose will be N cross N.
Is this lecture related to like when you normally do all these algorithms like PCA, you normally take X transpose X or X transpose. So when you're like the example that you use movies versus customers, when one of it is large, you take the other one so that your computation becomes better, right?
Exactly. I always say understand why. Otherwise, you'll just memorize without having relation to. By the way, if you are interested, somebody was asking question, are we talking about automated recommender system? No, but this is used in automated recommender system derivate. You experience it on a daily life. You open Netflix, you see it. This is what is going behind the scene. If you are really interested, there is actually a paper written by Amazon who actually pioneered this. It was started, and 30% of their business comes from this, by the way. So it makes tons of money for them also.
No, but actually the very, very high level intuitive and the perfect version of recommender system understanding is exactly your pixel thing that we did the other day. So all you do is solve the simultaneous equations. How you do it? You do it using SVDs.
So pixel is actually a recommendation.
Yeah. Pixel
Are
is
you
a
going to
recommendation.
go from a movie angle or are you go from customer angle? Ultimately,
Correct.
it's I from J. Are you going to go from row or column? Ultimately, it'll give you the answer. But if I go with the A transpose in this case, I have to do a 10,000 cross 10,000 matrix. The other one will be 100 cross 100. So I'll get faster answer.
So the idea is to finally get this Q, whatever, S lambda S transpose, Q lambda Q transpose only. So that is what tells you that some of the eigenvalues you can ignore in the corresponding rows and columns, and then you see what comes as an entry there. Right? Oh, that's a surgical process. But at the end of the day, you're just trying to figure out what is where. I mean, what should be the value if you ignore the details, and that value will tell you the recommended pixel value or the recommended rating of a movie of a person who has not watched the movie. See, there are many fronts in which we can see linear algebra, and that sometimes can get confusing. One is you see linear algebra as your geometric interpretation. One. Number two is you use it for computational ease. Two. Normally, 1 and 2 have different intuitions.
Yeah.
Okay. 3, at the end of the day, you're trying to solve some problem and model it as a matrix and then use some computational technique. These 3, I at least have not figured out a thread that stitches all 3. It always appears as different things. For instance, this matrix of recommender system is actually not a linear transformation. It's a stationary matrix. You cannot see it as a linear transformation. Right? But then if you see it as a linear transformation, you get all the geometrical interpretations.
Actually, it should be seen as a subspace because it's like the front page picture of Professor Strang, right? So because
the 4 fundamental subspaces helps in at the end of the day, it's all row space, column space, null space, and left null space only. But then if we interpret it as a transformation.
Correct. So what happens in
but I would like to quote whatever you said, Devasmith, a while ago. It's all about the application. So it's about what do you want to do. Based on that, we invoke different versions of its meaning and then resolve it at the end of the day. For instance, pure factorization. There are so many applications. In fact, I can tell you 2 applications where they are applied, but the end result is completely different.
Yeah, sir, I will actually share I'm not in WhatsApp. I'll find that paper and circulate it to everybody. Actually, it's very interesting, right? So read that paper.
Amazon one.
Yeah, and then we'll relate it to this. So what will happen is there are pros and cons with each approach also. So for example, very practical, let's say you are e-commerce portal, you're introducing a new product. So, let's say you are, I think there are Zara. Let's say you are a data scientist for Zara. What is the specialty of that business? Is they introduce a lot of new designs or SKUs or product every season. So
now, what I can recommend, Devasmith, is these things are now available in a beautiful form of textbook. This book called Mining Massive Datasets is freely available, and it has all these details.
So who are the authors for this?
Georg Leshkovec and I think Ullman.
Ullman is the famous guy, yeah.
And Rajaraman, if I'm not wrong. Someone can Google and post the link to the.
Ullman is very good, yeah. I think he has written another book. I'm not able to recall. He has written another great book.
Formal languages, automata theory.
What is the name of the book, sir?
Automata, yes.
Compilers also.
Yeah.
That's right. The name sounded so familiar. Theory of automated theory as in theory of computation, right?
Correct. Theory of computation.
What is the name of the book?
Mining Massive Datasets. I have written it on the
mmds.org.
Oh, is it?
I mean, they have a website also. These guys are all from Stanford. Ullman is from Stanford. Yeah, CS3.
Yeah, Georg Leshkovec, Anand Rajaraman, and Ullman. Correct.
Yeah, this is.
So this book is a good retreat, although he doesn't give a lot of intuition, but it's easier to read than than let's say paper. So whatever paper that you're talking about, Amazon's recommended systems, if I remember it right, this some 10, 20, 10, 15 years ago.
Yeah, absolutely. And it has gone through evolution also. It also talks about the evolution.
Oh, I see.
Yeah. Because it started simple and then I'll see if I had bookmarked it. I'll find and share it.
This was a quite interesting discussion. We discussed a lot of
This is
things.
what happens in Codasci, right? It's like a big Monte Carlo markup chain. You don't know what is going to be talked in next minute, and we just keep transitioning. We don't know
Yeah.
where we end up, and it's every time we are multiplying a transition matrix with each conversation.
Okay, I didn't get that. Like transition matrix in the sense you're shifting from
The conversation is going from one state to another, right? But depending on
transition. Okay, in that sense, yeah, okay.
so the topic will
Yeah,
change.
this is a different version of I guess, that you shared. Fourth edition is the recent. That is available as different. Is it?
I guess there is video lectures on this topic as well, I guess, on YouTube. Lecture. Most probably from a Stanford.
Where got disconnected?
He's reconnecting.
No, I'm very much here. Am I audible?
Yeah,
Yes, sir. Now you are audible.
Am I audible?
Yeah.
Yes, sir.
Yes,
Now
sir, yes, sir.
Acha. I was saying that this book's fourth edition is really good. I think you have shared an older edition of the book. I don't know. Just check, Ishan.
Yes, sir. I'm checking.
Yeah, in this, the recommender system is really awesome. Right? It's like, I would say this is the best reference so far. Still, it has some issues. I at least am not comfortable with the book because the authors don't seem to use linear algebra right. They somehow assume that people do not know linear algebra much. And hence leave out on many details. If you see 9.5 of the book that Nishan has shared, page number 337, the Netflix challenge is explained in a very superficial way. And 9.4 should be, wait, there should be a separate chapter on dimensional reduction. Where is it? Okay, 11th chapter. Is a good treat.
11th
I would
chapter.
suggest as part of Coder's we must be able to finish
Yeah,
this.
sir, definitely. This is why we exist, right? Yeah. So
Maybe I'm sure Devasmith is very thrilled seeing this book.
I mean, I've read the other book of Ullman, Jeff Ullman. When I heard, yes, I think he
Is it
has written it with Trevor Hesty and the other famous book, Machine Learning. So that's how it. These guys are all.
No, that is not Ullman. No, that is statistical.
Statistical
learning.
Elements of statistical learning.
Elements of statistical learning. Yes. वहाँ पे Ullman नहीं है, if I'm not wrong. Check. I don't know.
Maybe I read it in another book. I have forgotten.
No. Ullman is famous for compilers and formal languages, theory of computation, whatever.
That I'm less likely to read because my Euclidean distance from such subject is very high.
Very high. Achha, very.
Yeah.
Anyways, guys, I think take it up as a challenge to simply skim through this book.
Yeah, I think we have to read it.
It's Friedman, not Ullman. Yeah, man, maybe that right.
Friedman. Who can forget Friedman, the guy who invented what is that? Salford systems, the algorithm which is called random forest. Who can forget it?
Random forest.
And Leo Bridman, the other genius at Berkeley. These two are geniuses. The original code was written in Fortran. I remember when I was in graduate school, we wrote, ran those Fortran codes. Fortran 77 to be precise, F77 on Linux systems.
What is ESL, Bharat Shetty?
What is it?
Bharat mentioned something there. What is ESL?
think elements.
Elements
Oh,
of
elements of
statistical
statistical
learning.
learning. Okay.
Yeah.
Oh, is it? There's a new version of ESL, is it? I see. I didn't know.
It's like you're eating rasgulla, you just added little bit more sugar syrup. All are sweets, except you'll get diabetes faster.
Diwali time.
Right. So, guys, can we do a small exercise? Are you people on Twitter? Even on Twitter?
Yeah, I'm on Twitter.
It's
Yes,
called
Can you
X
see
these
my
days.
recent timeline where I posted about I'm trying to see the best way to understand Kalman filter, and a couple of links came about as a
Sir,
reply.
I don't follow you on Twitter. Like, I'll follow you.
Here
Let me give you my
you
handle.
should follow. X.
But Twitter is really a great resource these days. You don't end up wasting a lot of time there if you don't follow unwanted people. And for science and research, it's really good. The pointers I get from Twitter, oh my God, I don't get anywhere else.
Yeah, Twitter is fantastic in that regards. Even if we follow
Yeah, that way.
standard science
See,
science
all
journals, we know where the world is heading.
ARC,
Exactly, absolutely.
arxiv.org. That's the, you go there, you search all papers, you'll get.
So, what's your Twitter username?
No, I think our friend has just now shared. Bharat Shetty has shared, if you can see. Correct, Bharat Shetty, this is the one.
Bharat is
And two
like
people,
the-
Janaki and Pooja, have shared two links. And try reading this up. Let's see whether you people understand or not. Because things cannot be easier than this. Okay, choose one thing, maybe the second link. Can someone post? Bizarre.com. I think I myself can post. Copy link.
Pooja V answer.
Huh?
I can't read. Okay, you have to logged in. Okay. All right.
You're making a Twitter account.
Okay, look at this. Can people try reading this when you're free?
I think it's good. I need
Which
to
one?
find
Can you
it.
post a link, sir? Oh, okay, I see. Kalman filter works in
Go slowly. Let's see. Let me see how you people can read this. Finish this article maybe. It's a little lengthy, but I'd like to see how you will understand this. I'm preparing notes for this. I'm completely clueless how to start this because I find it very trivial, very obvious, but I cannot explain this because see the idea of covariance, the idea of I think even canonical form one can use, but then simple normal distribution, how to quickly explain that independently without making people
and
undergo
explain
stacked
normal
or
distribution easily to normal people.
Yeah. See, that normal is easy, but the formula is like explicitly used here. Well, why don't you people read this up, like paragraph by paragraph together in group? Try it for the next half an hour if you are awake.
Yes, sir.
Yeah. We can read it row by row, basically in a matrix. So no problem. Each paragraph is one row. The one thing is this author definitely makes it exciting. I have to tell you about Kalman filter because what it does is pretty damn amazing, right? So you just get excited just for the first time. So
The one line is that a Kalman filter figuring out the orientation of a free floating body by looking at its velocity.
surprisingly few software engineers and scientists seem to know about it. That makes me sad because it's such a general and powerful tool for combining information in the presence of uncertainty. At times its
You are
ability.
not audible, sir.
But why it makes him sad? He should be happy.
He should feel
No,
privileged.
he says not many understand. That is why I'm sad.
I mean, Okay.
A few software engineers seem to know, but okay, that is what is sad about, right?
See, generally in English, a few
It's
means
so
very
obvious,
few.
people should know it. Yeah, he's sad that people don't understand it. Okay, got
It's
it.
very London, UK English. Surprisingly, few software means no software.
Got it.
Uh,
Now, when you combine information, so we studied in stats one, I have a random variable X and a random variable Y. What is the distribution X plus Y? When you know the mu and sigma, right? Some of the things we have seen, it's not like we haven't. So that is actually combining information, X and Y.
Like that of combining two tables with some common link.
At times, its ability to extract accurate information seems almost magical. And if it sounds like I'm talking this up too much, then take a look at this previously posted video where I demonstrated a Kalman filter figuring out the orientation of a free floating body by looking at its velocity. So you have a dead body in a river and see where it is going.
Do you want to see the video?
Yeah, video.
I think it'll be a
Now
very
we are
small
doing
demonstration.
what do you call it?
We can't hear the video when we play it on Zoom. Like even if you play it,
That's all.
yeah. I've tried
We
it.
can all watch the video then.
The
Yeah,
link.
yeah. I mean, we all had the
That's
link,
what
and
I
then
was
we can
telling you
watch it.
people.
And
It probably is a good idea for you all to watch it later because there's no significant value addition to this article from the video.
Okay.
You can just start off from what is it?
you can use Canva filter in any place where you have uncertain information about some dynamic system, and you can make an educated guess about what the system is going to do next. Even if messy reality comes and interferes with the clean motion you guessed about, the Kalman filter will often do a very good job of figuring out what actually happened. And it can take advantages correlations between crazy phenomena that you maybe wouldn't have thought to exploit. Okay, systems which are continuously changing. Yeah. Okay, so
Light and memory. So essentially, like they don't keep too much of history, so they keep.
that day we discussed, something like we discussed something related. We did start our discussion on Kalman filters, right?
So think of like a stock price. So today's stock price is only depends on yesterday, and that's it, or maybe day before yesterday, but not what happened a month ago, because month is too long. A lot of things have happened. It's no longer valid, right? So this is where you kind of think of like a moving average, where I have my attention window is a very small window. Beyond that, I don't need to care about, memorize about it and all that. And I think that's a very fundamental thing. It's also used in neural network, particularly for time series data. So for degree level, it will come up. Yeah, it's continuously changing. The light and memory, which is all of us are.
Oh, yeah, like you said, it
Human
only
beings are.
depends on the previous state.
Yeah. So it is good for computation, right? You don't want to memorize everything. So it's also good from a computation standpoint. You don't have to memorize all the previous states, right?
Yeah, you don't need a lot of
Any history
memory.
other than
That's
the
what
previous state, they're very fast. So that means it's very well suited for real-time problems and embedded system where information is coming in. Think about IoT and all that. Things are coming in, right? So you're only keeping a moving window when kind of doing all your computation, edge computing and all that. It's very similar. Okay, the math for implementing the Kalman filter appears pretty scary and opaque in most places you find on Google. Okay, so we don't go to Google then. That's a bad state of affairs.
One small
Bing?
request, guys. One small request, just so that you people go ahead with confidence. Do you all have Gilbert's Strang book?
Yes, sir.
Yeah.
Can you go to index and read Kalman filter to figure out where is Kalman filter in the book? It will only take 2 minutes for you to read Gilbert Strang's version of Kalman filter. He paraphrases it in 3 lines.
it's linear algebra and its applications mostly, right? The second link probably.
Gilbert Strang graph. Linear algebra. अच्छा हो ठीक है था
I can't find it in this one. Am I looking in the wrong?
Can we access this drive link?
Yeah. I mean, if you have a ITMBS degree ID, you can access this.
Oh, okay.
You are not audible, Maria. You are not audible, Maria.
Yeah, my internet is bad.
Perfect. You guys nailed it. This is the place. Can you people take a look at it? It really takes a genius to, mention it in such a small. Oh, he writes it as an exercise problem, is it?
Yeah, the first time he introduced
Okay.
it, maybe.
No, it's not exercise. I think it's observation, right?
Let's understand this question 33. So you know the old average of 999 numbers. So when a new number arrives, check that the new average is a combination of X old plus, yeah. So you have to get rid of the, yeah, I see. So basically how much it's changing the average by, right? So that's the, yeah, got it. Yeah, makes sense.
Suppose you know the
He's
average X
finding out the gradient, I guess, like gradient of change.
Someone mentioned when we discussed
Not audible, Maria. You are not audible.
Because he okay.
Yeah, sorry. Why is it gradient?
No, it's gradient of change. I was just telling that it's gradient of change because you can see that this exact kind of representation. He's trying to get this. He's trying to get the slope of it. If or the change that the B1000 is making on the existing one. That is what is B1000 by 1000 minus this entire expression that is already the remaining average. Right?
Yeah, but this 1000 is being multiplied inside as well, right?
Yes. So
Yeah,
let's say there are 999 numbers we had. The average is 10, average is 100, right? So that means you can generate 999 numbers and the average is 100. So each number could be anything, right? Some numbers are above 100, some numbers are below 100. But when you take average is 100 for the 999 numbers. So what it is saying is if we get a new number, how much it is going to change my existing average. My average was 100. I add the 1000th number, right? So what will happen if I kind of look at it? I have to add up all the 1000 numbers and divide it by 1000, right?
Yeah.
Right. So what it is saying is instead of saying that, it said, no, let me not do that. I'll take the new number minus the average, which is essentially nothing but sum by 100.
Yeah.
And the deviation. So basically it's saying how much it is deviating from the current mean. This is almost like physically, I have a center of gravity and it's stable. Now I put a new marble. How much is going to change my center of gravity, basically, right? So that's basically what it's saying. So then what you do is, because now we'll have 1000 elements, 1 by 100, and how much it is going to be deviating from the previous average. So the new number minus the old average. B1000 new number minus the old average. That's all it is saying. We get this kind of questions in quiz 1 of math 1, I remember from last few years ago.
Yeah.
They'll give some numbers and how much, all that.
Why is it called a filter?
Why it is called?
A filter.
Oh,
Atharva,
filter is something it used in daily life to filter the dust, filter the noise, so when you're looking at time series data, it has pattern and noise. It will get rid of the noise, so you can get the pattern, then you can put a model through it. COVID virus is filtered through the mask, Kalman mask, to get rid of COVID virus, which is the noise.
So you subtracted from the old mean. So let's look at a few possibilities. If B1000 happen to be the same as the mean, and this would just be 0.
It will not change, so the entire thing is 0, so it will not change. That's great.
Yeah.
That's a special case. But
Yeah.
most of the time, the new number will be either below the existing
Below
average
or above.
above. If it is below, it will be negative number, so it will pull the
Yeah.
average down. Otherwise, if it is a higher number, it will pull the average up. So we have actually studied in arithmetic averages. What will happen to a rolling average of numbers? That's basically what we learned.
I think this is what sir wanted us to do.
Dynamic least squares.
The great algorithm in dynamic least squares. The word dynamic means that new measurements bk keep coming. So this is like a time series data.
Yes. So we had 999 numbers. Now B1000
The
appears.
new-
So that's the
yeah.
new data.
Yeah. So the best estimate x hat of k keeps changing based on all of B0 up to bk. More than that, the matrix A is also changing. So x2 hat will be our best least squares estimate of the latest solution xk to the whole history of observation equations and update equations, state equations up to time 2.
So this is the initial. Then what is the data? You have data is represented as B, right?
Yeah.
What are we calling?
Yeah, B1, B2, B3. So the new measurements bk, right? So B0 to bk will be our measurement. And A is the matrix which is changing with time. And our x hat will keep changing based on that. So what is F0? F1 and F2 onwards?
First matrix you apply to x0 to get to x1, then apply on the matrix. But B1 is new data. You apply. B1 is a coefficient. X1 is what? X1 is the.
Kalman idea is to introduce one equation at a time. There will be errors in each equation. With every new equation, we update the best estimate x hat A for the current xk. So this A1, x1 will be our x hat k, right? Because it's like a least squares estimate for the value. Right? That's what we've been seeing all this while. We're trying to project, or is it the other way around? Yeah, we're trying to project.
See, if we look at the mate all the way down the new, it's saying A0 x1 equal to B0, A1 x1 is B1, right? Like that. So those are the matrices we need to multiply to get.
That's the matrix change part, right? So we're updating the matrix in this step, which is here we are setting x1, and then we are using x1 to update our matrix A1 given our B1, right? That's what I understand them here. We know B0 and B1.
What is
X1
that F matrix you're saying? It's estimated. What is the notation for F? Maybe a little top, must have mentioned. What is F?
Okay. Yeah.
Uh,
So what it says is that we start with Ax is equal to b, and we keep on in kind of improving and also keeping the record of our improvement in the form of matrix or vectors, whatever we call it.
I can't understand that.
It is saying x new equal to
Mhm.
f old into x old. Okay. So is it like a ratio between two, the new divided by the old? That's the f, like a ratio, like a common ratio in a. We have seen that in GP, not like it's a sequence. So anyway, interesting. So f is the factor that you multiply to the old number to get the new number.
So friends, feel free to continue discussion in this mode, but my suggested path would be a little, whatever small 3 lines that you read, that is more than enough. Now you can move to that blog.
Okay.
This is a little heavy on the mind, at least in my opinion.
Yeah, I will read it. That blue is the great one.
Yeah. I'm learning that now, actually.
Yeah,
Linear statistical.
Mr. C.R. Rao, who
Yeah.
just passed away recently. He's the chief
Oh, okay.
of that.
Okay.
Here, what? Didn't get it.
So that best linear unbiased estimator. So
Unbiased
they created a
estimator.
lower bound. How do you know an estimator is the best estimator, which has basically
Oh, CRF did that, is it?
yeah, it is actually Kramer Rao lower bound. It is two gentlemen, Kramer, Professor Kramer, the Kramer's V guy, and
the Kramer's of Kramer rule. Yeah.
yes, in determinant matrix.
Yeah, I met C.R. Rao when he was 100 years old, but very recently passed away. It was
Yes.
102, no? 101 or 102.
Yeah, I also visited his lab in Penn State. It's in a small city called University Town in Pennsylvania.
Oh, I see.
Yeah, this is the gentleman.
There's an institute in his name in Hyderabad.
Yeah.
He's I think the first, he was associated with ISI.
He was director of ISI for a long time.
Yeah. In fact, he relocated to US to live with his daughter. So that's how you ended up getting associated with Pennsylvania State University. He's like a stalwart. He was a student of R.A. Fisher, Ronald A. Fisher, who is the father of modern statistics.
Yeah.
From England.
So what we have to keep in mind is that it's kind of like
It keeps on improving, and at the same time, it keeps a record of old, entries.
But without memorizing them,
too
like
much memory. It's only using one old.
That's
one
why,
state. One state.
and we can kind of relate it with the cricketing approach. You have to win the game, but you have to play only one ball at a time.
Yeah. Exactly.
Or other ways, let's say you are finding batting average of a batsman. Every innings, after every innings, you are getting a new score and you're updating the batting average of that batsman. There are two ways. You can remember all the scores of all the innings that the batsman has scored, or I will just store the average and how many innings. So in two variables, I can update. If the new score is above average, batting average is going to increase. Or if the new score you get out for a less score than your average, your new average will be down than the old average. So it's basically as simple as that.
It's very suitable for real time, problem.
Yeah. The moment we relate this theory to something that we can relate to, then I think the life will be interesting. Otherwise, we'll always be wandering in the abstract world.
See, it mentions embedded systems, like I was kind of mentioning about this a couple of days back. How in electronic system we keep a record of error that comes up in every loop.
Yes.
The math for implementing the Kalman filter appears pretty scary and opaque in most places you find on Google. That's a bad state of affairs because the Kalman filter is actually super simple and easy to understand if you look at it in the right way. Thus, it makes a great article topic, and I will attempt to illuminate it with lots of clear, pretty pictures and colors. The prerequisites are simple. All you need is a basic understanding of probability and matrices. I'll start with a loose example of the kind of thing a Kalman filter can solve. But if you want to get right to the shiny pictures in math, feel free to jump ahead. What can we do with a Kalman filter? Let's make a toy example. You have built a little robot that can wander around in the woods, and the robot needs to know exactly where it is so that it can navigate. Kind of GPS, I guess. We'll say our robot has a state xk vector, which is just a position and velocity. Okay, there is a vector and there are two elements to it. One is the position vector and another is velocity. Fine. Okay, and it says that it is a state. Okay, so it is kind of dealing with what we have for an electron in an atom. We only
where you are now and where you are going.
Where we are going. Okay,
Which
correct.
way?
Okay. Note that the state is just a list of numbers. Okay, good. About the underlying configuration of your system. It could be anything. In our example, it's position and velocity. But it could be data about the amount of fluid in a tank, the temperature of a car engine, the position of a user's finger on a touchpad, or any number of things you need to keep a track of.
Basically, it's a tuple of some. It's just a tuple
of some numbers.
Yes.
Okay. Our robot also has a GPS sensor, which is accurate to about 10 meters, which is good, but it needs to know its location more precisely than 10 meters. There's lots of gullies and cliffs in these woods. And if the robot is wrong by more than a few feet, it could fall off a cliff. So GPS by itself is not good enough. We might also know something about how the robot moves. It knows the commands sent to the wheel motors. And it knows that if it's headed in one direction and nothing interferes, at the next instant it will likely be further along that same direction. But of course, it doesn't know everything about its motion. It might be buffeted by the wind. The wheels might slip a little bit or roll over bumpy terrain. So the amount of wheels have turned might not exactly represent how far the robot has actually traveled. And the prediction won't be perfect. Okay, so there is going to be some slips and effect of winds and all. So we cannot rely on the data being furnished by the motor itself. How much revolutions and those stuffs. The GPS sensor tells us something about the state, but only indirectly, and with some uncertainty or inaccuracy. Our prediction tells us something about how the robot is moving, but only indirectly and with some uncertainty or inaccuracy. But if we use all the information available to us, we can get a better answer than either estimate would give us by itself. Okay, then either estimates would give us by itself. Either of them being by sensor or prediction. Fine. Of course, the answer is yes. And that's what a Kalman filter is for. Okay, how a Kalman filter sees your problem. Let's look at the.
Yeah, so I think here we can think about such examples where using two estimates will help give us a better estimate than just using one. Right?
One estimate, correct.
I think if you think about, let's say, I think we did this one thing, right? There was about subjects and trying to predict the score of one subject given the data of just so we try to see the English marks. You can estimate it with just your maths mark. Or
Yeah, the closest we have all learned is in physics, standard 12, 13, right? So there's something called a measurement error, a vernier caliper, if you remember, calibration, instrumentation, right? So you are measuring something, weight, height, length, but it has some error and you don't know what it is. So it's like that. So GPS is working, but up to 10 feet. So it will say that you are at this lat and long, but it may be off by 10 feet. That's what. So that's the error. So if you look at the error compared to the height at a satellite, it's probably minuscule. But when you project that on the Earth surface, it's 10 feet. So this is where it is. But it knows that if next step, you don't know. The second thing is you also don't know what the error is. It is somewhere between 0 to 10 feet. That's also uncertain. But you know that it's not exact. Kind of getting an approximate reading.
what
So
is
it's
our
like-
prediction in this sense?
Because the prediction is based on a model, and the model is using the data, and the data has uncertainty. So what it predict is also a bit uncertain because, so remember, so let's say the real data is X and there is some error called E. But the errors are also like, first actual data was X1, but what you observed was X1 plus E1.
Yeah.
Similar, next data you observed was kind of X2 plus E2. But what we observed is actually together, right? But we don't know how to decompose what is the truth and what is the error, because that is not uniform. That's kind of course, we know the upper bound for E is 10.
Yeah. 10 meters.
The only thing we know.
So we kind of know something about it. I mean, we have an upper bound about its variance. That's all we know. Kind of.
I think in this, I mean, so far, what you have seen, yeah.
Yeah. You want to go
Okay.
ahead?
Okay, how a Kalman filter sees your problem. Let's look at the landscape we were trying to interpret. We will continue with a simple state having only position and velocity. That is x is equal to pv. That is pv being a vector. We don't know what the actual position and velocity are. There are a whole range of possible combinations of position and velocity that might be true, but some of them are more likely than others. Okay.
Is that because
Clustering thing, huh?
So what is happening is, you see, the P is basically, kind of position, but think about it, it can be, P is actually a sample from underlying distribution, and it's just a random sample from that underlying process. We could have picked either from the left side and right hand side of the distribution. That's all it is saying.
you come from anywhere? Yeah. It's more likely that.
So that means it's not a symmetric distribution. It is slightly skewed or whatever, right? So that means it's less likely to be on the left hand side, more likely to be on the right hand side of that. So that means when we look at that point, the point is there, but then and it's a joint distribution between two parameters, right? What you see here is if you take that white space, so this is a probability, all the probability added together is 1. But if I ignore the position, which is the y1, then I get the marginal for velocity. But if I ignore velocity, I'll get the marginal for position. But there is a correlation between these two variables. That's why they're kind of in a circle. But if it is, so that means it can be anywhere in that ellipse. And it's 1 point. But one thing we know for sure, it is more likely to be on the right hand side of the ellipse than the left hand side of the ellipse, because that is what the marginal distribution of velocity tells me. So my marginal distribution of velocity is actually left
Right.
skewed.
Okay, left skewed. Okay.
Yes.
Because you're more.
Left tail is longer than that is all I know. Similarly,
Okay,
I can also
till-
draw inference for position. I mean, this is again something we have learned in stats 2, probably joint distribution.
But
Okay.
I mean, okay. How do you say that the velocity is left skewed?
So because it is saying very likely, that means my probability mass is bigger on the right hand side compared to the left hand side.
The tail is bigger on the left hand side. That's why left is skewed.
No, this looks like this the legend for the.
See, the heap is coming on the right, of course, but where the tail will be larger on the left hand side, right?
So left hand is longer, and then after that it pops up. Like when you draw the PDF on this one, you have to have a longer left tail, and then your mass is concentrated on the right hand side. That's what it is saying, right?
No, but okay, intuitively I would say it should be right, because okay.
I mean, when you have more probability on the right, your left tail is longer, hence it's called left skewed. That's all.
Just the nomenclature thing, I guess. Okay.
Makes it a little interesting. Otherwise, it will have been a circle, right? So that's why it's an elliptical.
Okay. The Kalman filter assumes that both variables, position and velocity in our case, are random and Gaussian distributed. Okay.
An assumption. Yeah.
Each variable has a mean value mu, which is the center of the random distribution, and its most likely state, and a variance sigma square, which is the uncertainty. Okay. Mu is in the center, variance in the position sigma square. Okay, this is the okay, we have two sigma squares for position and velocity. Fine, good. In the above picture, position and velocity are uncorrelated. They're not related. Fine.
But they're
Which means
right? You make it angle, then correlated.
they're independent of each other.
Yes.
Okay. In the above picture, position and velocity are uncorrelated, which means that the state of one variable tells you nothing about the other might be. The example below shows something more interesting. Position and velocity are correlated. The one sir was talking about. The likelihood of observing a particular position depends on what velocity you have. Great. This kind of situation might arise if, for example, we are estimating a new position based on an old one. Okay, if our velocity was high, we probably moved farther, so our position will be more distant. If we are moving slowly, we didn't get as far. This kind of relationship is really important to keep track of because it gives us more information. One measurement tells us something about what the others could be. Okay, it's all about correlation.
Yes.
And okay, we have got a data and we can kind of transform that data into correlated data. And the data initially may be, independent of each other. And
we want to be careful. When we say data, we are talking about a tuple. In this case, when we say data at time t0, I'm getting position at time 0, p0, and velocity at time 0, which is v0.
Yes, sir.
Then when the thing moves and we observe again, we get the new position p1 and velocity v1.
V1,
fine. At time 1, and let 1 be 1 second unit interval.
Okay.
So what it is saying is, if I observe this robot for, let's say, next 100 seconds, what will happen? I'll get 100 positions, I'll get 100 velocities.
Yes, sir.
These are components of my tuple. What it is talking about is the position is a random variable x1, and velocity is a random variable
v1.
And then what is the correlation between these two random variables, which are part of the same tuple? So
okay.
This is across time.
Okay, since they belong to same tuple, that is the relation between them. Okay. Okay, so this kind of relationship is really important to keep track of because it gives us more information. One measurement tells us something about the others could be, and that's the goal of the Kalman filter. We want to squeeze as much information from our uncertain measurements as we possibly can. This correlation is captured by something called covariance matrix. Great. In short, okay, great. We must learn what is covariance matrix. This correlation is captured by something called covariance matrix. In short, each element of the matrix Ij is the degree of summation of Ij is the degree of correlation between the ith state variable and the jth state variable. You might be able to guess that the covariance matrix is symmetric, which means that it doesn't matter if you swap I and j.
Covariance matrices are often labeled as kind of summation. So we call their elements summation of ij. Okay, this is some kind of, I guess, what do we call it? Latin notation.
Yeah.
Okay, so
Capital
covariance.
C.
Okay, so the kind of crocodile's mouth is the kind of the shorter arm of the ellipse, isn't it? Okay.
Okay.
So
Um,
I'll read it again. One second. I'll read it again. This kind of relationship is really important to keep track of because it gives us more information. One measurement tells us something about what others could be, and that's the goal of Kalman filter. We want to squeeze as much information from our uncertain measurements as we possibly can. Fine. This correlation is captured by something called a covariance matrix. In short, each element of the matrix, ij, is the degree of correlation between ith state variable and jth state variable. Great. So every element of the matrix is telling about the degree of correlation of every tuple. ij being the nomenclature for it, their position, and on which tuples, what is the number of that tuple. That's great. You might be able to guess that the covariance matrix is symmetric, which means that it doesn't matter if you swap I and j. Fine. Covariance matrices are often labeled as this, so we call their elements this ij. Fine. Okay. Describing the problem with matrices. We are modeling our knowledge about the state of a Gaussian blob. So we need two pieces of information at time k. Fine. We'll call our best estimate sk cap. The mean elsewhere named mu, and its covariance matrix pk. Fine. Okay.
So the diagonal element will be containing the variance of the variable, and the off-diagonal elements will contain the covariance.
So this
Okay.
is the variance.
It is
of
called
P,
variance covariance matrix.
and the diagonal elements have the variance. And
Variance of each random variable, because it's two variables here, so you'll
Yeah.
get a 2x2 matrix. Diagonal is P of P. That means it's covariance with itself. So that's basically variance of P position. And the sigma VV is variance of velocity.
Okay.
And
Okay.
sigma PV and sigma VP are the same. So it is covariance of velocity and position. So it's like sigma xy minus x bar y bar divided by sigma x dot sigma y. Starts one.
Okay. Of course, we are using only position and velocity here, but it's useful to remember that the state can contain any number of variables and represent anything you want.
So in this case, the tuple was of dimension 2, we are getting
2.
2x2. If our tuple had k variables, we would have get a k cross k matrix, and we'll have k choose two pairs of correlation covariance.
So the diagonal elements, of course, would
Always be the variance of k variables.
K variables. Fine.
And
Next.
one thing, notice, linking the point to the previous concept we learned, it is a symmetric square matrix. That's
Symmetrical square matrix. Okay. Next, we need some way to look at the current state at time k1, and okay, we need some way to look at. First of all, we need to look at the current state at time k1. Fine, and predict the next state at time k. Remember, we don't know which state is real one, but our prediction function doesn't care. It just works on all of them and gives us new distribution. Great. We can represent this prediction step with matrix Fk. Okay. It takes every point in our original estimate and moves it to a new predicted location, which is where the system would move if that original estimate was a right one. Great. Let's apply this. It's basically coming down to linear transformation and all. Okay. Let's apply this.
So
And-
basically what it was it was in a space called P cross V. It is taking a tuple which is containing Cartesian component of P cross V and it's mapping into another one. Basically, that's what it is doing. And Fk is the linear map between
Yep.
these two vector spaces.
Yep. Okay. It takes every point in our original state estimate and moves it to a new predicted location, which is where the system would move if that original estimate was the right one. Let's apply this. How would we use a matrix to predict the position and velocity at the next moment in the future? We'll use a really basic kinematic formula, that is pk is equal to pk minus 1 plus delta t vk minus 1 is equal to, I guess, v bar is equal to u plus at, I guess it is, or something like that. S is equal to ut plus
So
half,
what
it
I'm
is equal
saying
to.
is your previous position was Pk minus 1. And if your velocity was Vk minus 1 and the time elapsed is delta t, that means you have traveled the time, which is delta t multiplied by your velocity that it was. So that's the distance you have traveled from the previous position.
Okay, simple, kind of
Yeah.
representation of it, that we have come to a new position, and what basically it is that previous position plus the time elapsed and the distance traveled in that elapsed time.
Correct.
This is nothing but distance because time into velocity.
And of course, the velocity is not changing. So the Vk and Vk
Acceleration is zero.
acceleration is 0. So Vk is equal to Vk minus 1. In words, we write it as 1 delta t 0 1 and multiply it with x cap k minus 1.
So that
Okay.
Matrix, when it's multiplied to the previous state, it's new. So that means this is a transition matrix. So when I multiply this matrix to a state, a vector in a state, it gives me the next state. So it is allowing me. So when I multiply that matrix, it contains all the transitions embedded inside it.
Okay.
You wanted to write that down. I think very nice. So we're taking a step. So x t minus 1 or k minus 1. Yeah. Which is equal to t k minus 1 and v k minus 1, right?
Yeah, position and vector velocity, yes.
Yeah. So this is our current
State. Current state.
And is this a predicted state or is this a
No, current state.
Current state, present, real-time state.
You apply a matrix to go to the next state.
Okay. So now
Predict a future.
So you'll apply a matrix called Fk.
Yeah.
To x to get the next state, which is Pk Vk. And how we got that magic is through.
Because we want Pk equal to
Pk minus 1 plus subscript. Pk minus 1, k minus 1 is subscript. Plus delta t is the time elapsed multiplied by the velocity, which is Pk minus 1.
Delta is inverted here.
My bad.
Yeah.
I'm used to
That is gradient.
And that is gradient.
And
velocity remains the same. Vk is equal to Vk minus 1.
This part somehow I'm not very. So the velocity remains the same over time, right? Okay.
So we are moving for
Constant
see. So it's like, you are going from position 1 to position 2 with uniform velocity. Fine. So your position is changing, but your velocity is not changing.
Yeah.
So, and what you are writing position as your previous position, that is your current position, and what your next position would be after delta t time. What you know is you are going to make your next calculation in delta t time.
Yeah.
So what you basically do is you multiply your velocity with the time and you get this distance. This is a basic speed distance formula. So there was your speed, and you kind of correlated your position and the speed with the help of time here. And see, and we are now representing this complete situation in the form of a transition matrix. 1 delta t and 0 1.
One thing we notice, it is a upper triangular matrix, just observation.
Correct. This is upper triangular matrix.
Again, trying hook to the previous concepts learnt. All these dots will get connected eventually.
So we will write xk equal to fk into xk minus 1. So
Yes.
xk is equal to this. So xk is equal to.
I never ever dreamt of writing in the kinematic formulas in the form of matrices. Multiplying matrices, I never dreamt of it. This is just next level, I must
It will
say.
all happen in this
It
lifetime.
looks so weird.
It will happen in this lifetime. That's the guarantee of being part of Codasci.
My goodness.
The impossible possible.
It gives goosebumps, really.
This is the same thing that we wrote about. Okay.
I came across a teacher, I told that to Chetan once. He told the complete batch in where I was there, he told me at end of the day, you are going to rise up the pyramid and everything is going to get connected. What today seems not connected, not so connected, and two completely different things are going to eventually get connected. And he actually told us, I don't remember the name. I was very young at that point of time. So he told that, okay, what after a PhD do you know? What is the degree you get after a PhD? So he mentioned of a program or kind of degree or something, or again, only.
Postdoc.
No, that was you do not kind of learn something new in that group or in that degree. You only experienced buddies come and share their experience. How they perceived the same thing, the same field in the same. They are all in the same field, and they all share their experiences and their approach towards their field. Although I don't remember, there is some kind of degree going on or some program going on where this happens. Anyways, so we are now very much clear, what do we mean by transition matrices?
They're calling it a prediction matrix.
Okay, prediction matrix. We now have a prediction matrix, which gives us our next state, but we still don't know how to update the covariance matrix. Okay. This is just one covariance matrix. We do not know how to update it, right?
We want to keep updating this until it's close to the real, population.
Yeah, what's happening is when you are doing it, this is after k steps.
Yeah.
You have k tuples and you have estimated variance covariance after k observations or k times steps has elapsed.
Yeah.
The moment you get to position, the new velocity, now your number will become k plus 1.
Yeah.
So those numbers will change.
Yeah, at that point, you don't want to keep storing the all the k plus 1. You want to somehow make it easier. That's what we're trying to do, right?
At the end of the day, the gist of the story is that your computer is not going to store a formula or do computation every time. Your computer is going to only store a data. So you want to you want to keep updating it so that
a single
single data, so that an algorithm takes it, gives yet another output, takes it, gives yet another output.
Yeah, it's like same bucket times this. You reusing the things from the bucket, updating it, making it better, and then I'm putting it back into the same bucket.
Same bucket. Better data being put every time and being processed.
Better estimate. Yeah,
better estimates.
I like this.
Yes, sir. So this is where we need another formula. If we multiply every point in a distribution by a matrix A, okay, then what happens to its covariance matrix? So that is the symbol of summation. I don't know what we call it.
Sigma.
Well,
Sigma,
Let's call it
capital
sigma.
sigma, right?
sigma. Okay. Okay, this is the formula. If we multiply every point in the distribution by matrix A, then what happens to its covariance matrix sigma? Well, it's easy. I'll just give you the identity. Covariance X is equal to sigma and covariance AX is equal to A sigma A transpose.
This is again starts one problem. If you take a bunch of numbers, calculate mean and standard deviation, right? So if I multiply the number by 2, all the numbers by 2, it's pretty intuitive that the new mean will be twice the old mean, right? Because all the numbers are doubled. But the variance will be 2 square, 4 times. Standard deviation will be 2 times. So in case of matrix, there are multiple numbers. The equivalent of square is pre-multiplied by A and post-multiplied by A transpose. And sigma is the original variance.
I can't see that clearly yet.
No, these questions are being asked in qualifiers. They ask this question, what will happen to covariance or what will happen to mean and all, you know?
Correct. Yeah, of course. This was actually starts one, I remember, long time back.
First 4 weeks.
Yeah, starts one.
Correct.
4.
Week 4, correct. Okay. So combining equation 4 with equation 3, we get we have xk and pk. Okay.
PK is our lambda. Is our covariance.
Position.
No. PK is the prediction matrix.
Sorry. Prediction
matrix.
matrix.
So the updation formula we got, right? So that PK is again because we are multiplying with FK, just like AX. You pre-multiply with FK and post-multiply with the transpose of FK. That's it.
Kind of a speedy formula, isn't it?
Yeah, I mean, you if you really want to understand, take a 2 by 2 box. Let's say my A is what? A is I'm going to increase it. My position I'm going to increase multiply by 2, and I want to increase velocity by 3. So if you do that, then you will see like what is happening really, right? So we can actually prove it. But anyway, intuitively, square means pre-multiply by A and post-multiply A transpose. You should see that it's actually kind of
squaring it,
and variance covariance will actually go in the, if you multiply by 2, the variance covariance would go to the factor of 2 to the power 2. The 2 to the power 2, we cannot say A square, so that's why we're saying A transpose.
We cannot say A square. Correct. External influence. We haven't captured everything, though. There might be some changes that aren't related to the state itself. The outside world could be affecting the system. For example, if the state models the motion of a train, the train operator might push on the throttle, causing the train to accelerate. Similarly, in our robot example, the navigation software might issue a command to turn the wheels or stop. If we know this additional information about what's going on in the world, we could stuff it into a vector called UK. Do you do something with it and add it onto our prediction as a correction? Okay, it's not going to follow a pattern anymore, or anything could come up at random. A new situation could arise anytime. For example, a missile is cruising and it encounters a stream of wind suddenly, and of course it's going to, there is a propulsion in one direction, and it is going to change its trajectory for a while if it's going to come across. And of course that was not predicted because suddenly this new external effect has come up. Let's say we know the expected acceleration A due to the throttle setting or control commands. From basic kinematics, we get Pk is equal to the older position plus delta t times Vk. That is again a position, new position, after time t, and acceleration and position as a result of acceleration. That is half at square.
So if you
Fine.
remember, displacement is equal to ut plus half at
Half
square.
at square,
The
yes, yes.
initial displacement. So u is here vk minus 1 because that is what the current velocity. And then half at square, half a little at square. We already know s equal to ut plus half at square.
And s is pk minus 1.
Yeah.
S is equal to ut plus half at square. Fine.
Now the accelerator is not 0. So the new velocity will be old velocity plus the acceleration plus the time elapsed. So now basically what happened, we started with a linear, now we got into quadratic zone with acceleration.
Correct. So we must know how data are kind of interrelated. We must also then how the
Yeah, previously it was one moment, now it is second moment.
correct. In matrix form, we write it as xk is equal to fk into xk minus 1 and delta t square by 2 upon delta t a.
Basically, we had already shown the first part of the left hand side. What we did is whatever we had done already with acceleration 0.
Now adding up to
a into the mix, we add half at square on the top for the position and add a delta t to the velocity. So essentially, whatever was there, I just add this extra thing on the right. So then it makes it work. So because we had already solved the previous problem, so it's kind of building on the solution to the previous assumption.
Okay, BK is called the control matrix, and UK the control vector.
Yeah.
Great.
Because it's a pedal, you're controlling the acceleration to the gas pedal.
Correct. For very simple systems with no external influence, you could omit these. Okay. Where there is no wind blowing, everything goes as usual. We keep we keep the scalar part to be 0 and things come back to normal. Let's add one more detail. What happens if our prediction is not 100% accurate model of what's actually going on? It's a big paper, I guess. It is 12 already. Should we kind of wrap up if you want? I'm okay. I can continue.
It's just getting started.
It appears that it's getting started.
Like s equal to ut. Where is the half ut square?
Correct. Because I saw this coming, the interest is getting increased and the time is also.
The acceleration was 0, now it's just starting.
It's just starting to pedal. We are just putting our
Let's
foot
take
on
a
the
poll
pedal.
on mood of people. Like, let's see.
Maria is there, Bharat is there, Shriram is there, Srivina is
Maria
there.
is saying good night.
Okay.
Shibine
They were wishing good night to Ankit. So they were wishing good night to Ankit.
Okay, who is actually the original one? Because we have a lot of transition matrices here. We have to look at who was the original one. All right, so good night.
I guess Maria is not here.
She is here. She is here.
Okay, she said good night at 51 itself.
So Ankit actually.
To Ankit.
Too tough to digest.
Say good night to Ankit. Okay, all right.
Okay, Ankit is gone. Okay. Maria was saying good night to Ankit. Fine.
Too tough to digest now. Okay.
Too tough to digest now, Sriram.
It's very raw things going on.
We have to break down the protein so that it can be digested well.
Yeah, but protein breakdown time is
cow
very
milk thing, what we get in Delhi.
We'll be discussing this again and we'll break it down slowly.
And there is kind of cream milk, and there is normal milk, and there is cow milk.
Skimmed milk.
Skimmed milk.
Skimmed.
Mother dairy.
2% fat.
2% fat. Smaller fats.
Yeah. By the way, your SBD is actually, if you boil milk, pour a little drop of lemon. It will condense everything into D cross D matrix, what you call a cheese and onion. Rest is water, which is small eigenvalues.
Eigenvalues, correct. All the
So
Nutrient value gets
all the
conserved.
calorific content of the milk, which is equivalent to area or determinant, gets condensed into the cheese.
And
Rest
cheese.
is all garbage. Now you can argue that is a small, minute calorie getting lost because you see strong droplets of white stuff. That's very small. Lambda. You can ignore it. By getting rid of that, you are not really reducing information. I always give example of what is dimension reduction or data condensation. This is what it is. Real life, we do it.
Sir, I must say one thing here. I've become a fan of your examples. I must say this.
Real
I
life,
must put it out there.
real life
Yeah.
examples, you know.
Yeah,
How physics becomes metaphysics.
hands
That is the
down
beauty.
best examples. Hands down the best examples.
You know,
It's intuitive, like human mind is all over. Nobody told you, just think, some, okay, when you observe, nobody told, okay, it is like this matrix. Okay, I'm not losing calorific value. I'm consuming that sweet without, but I'm getting rid of all the stuff, so I'm compressing. We are ultimately in the business of data compression. We want to compress data,
Right.
not lose value. Same thing happened with MP3 music. I want to store, you remember previously CD used to have 12 or 14 music until MP3 came in. After that, what happened? We could store 1,000 songs in
Thousands.
CD.
Right.
So was there a deterioration in the quality of the MP3 music? The answer is yes, but the deterioration was 2%, which is not going to make a huge difference to the human ear. That's all it is. That was the reconstruction error, right? So we saw that happening. It's just, we never related that, hey, it's been there since ever, right? MP3 music and everything. And that's the math they did.
Right.
Okay.
Acceptance of error.
you never forget the concepts learned this way. That is the best part of it. You always, your mind kind of goes back to, okay, this is related to milk decomposition.
I'm going to regret today.
Milk for matrix. Remember, M for milk.
M for matrix.
M for what do you call it? In life, I thought what motivation, right?
Motivation. Motivation. Milk is the motivation for matrix.
Sir, I just wanted to ask you one thing, that are we discussing something, or should I just stop the recording, because this is going to be there on YouTube?
Oh boy. Okay, let's stop.
Okay. Let's call it the day.
Let's